Hello, and welcome to the Air Systems Cleaning Specialist Certification Journey. In this chapter, we will establish the foundational knowledge and industry standards required to excel as a professional in HVAC system cleaning and restorative services. This course is an unofficial, independently produced study guide and exam preparation resource. It is not affiliated with, endorsed by, or connected to the National Air Duct Cleaners Association, NADCA, or any other official certification body in any way. All trademarks, including ASCS and NADCA, belong to their respective owners. This content is for informational and educational purposes only and does not guarantee success on any professional examination. Pursuing the ASCS credential is a significant milestone for any technician aiming to demonstrate mastery over indoor air quality and system performance. This course is meticulously designed to provide you with a rigorous understanding of the NADCA ACR standard, which serves as the global benchmark for the HVAC cleaning industry. By investing your time here, you are positioning yourself as a highly capable professional who understands the intersection of mechanical integrity and environmental hygiene. We will move beyond simple cleaning tasks to explore the technical nuances of thermodynamics and controlled airflow. You will gain the expertise to evaluate system health objectively, ensuring that every project you undertake meets the highest standard of excellence. This curriculum has been curated to address the specific technical requirements defined by the National Air Duct Cleaners Association, ensuring you are fully prepared for the certification examination. The ASCS credential acts as a testament to your technical rigor, signaling to clients and employers that you possess the specialized knowledge required to maintain safe and efficient air systems. Throughout this course, we will dissect the fundamental components of heating, ventilation, and air conditioning equipment to understand how they interact within a building envelope. You will learn the critical difference between mere dusting and comprehensive source removal, which is the primary cleaning methodology prescribed by the industry standards. We will also touch upon the essential aspects of safety, including OSHA requirements that govern work in confined spaces and the handling of hazardous materials. Our objective is to transition your understanding from reactive cleaning to a systematic, proactive approach that treats HVAC systems as vital support infrastructures for human health. You will see how standardized documentation and rigorous reporting practices serve not only to protect the facility owner, but also to validate the effectiveness of your technical interventions. To succeed in this field, one must appreciate the complexity of the indoor environments we service. We will focus on the foundational terminology, such as IAQ, static pressure, and negative pressure differentials, that will populate your day-to-day work environment. Mastering these concepts is not just about passing an exam. It is about developing the intuition needed to diagnose system failures before they cause environmental issues in residential or commercial settings. We will walk through the logic of project assessment, from the initial site walkthrough to final verification steps that confirm the system is clean and functional. You will learn why ignoring the physics of airflow leads to poor IAQ outcomes and how proper filtration and routine coil maintenance prevent costly system degradation. By the end of this program, the standard of professional ethics inherent in NADCA membership will become second nature to your workflow. We will also emphasize the importance of compliance, as you will be operating within a framework dictated by international consensus on clean systems. Understanding the difference between how one approaches porous materials versus metallic structures is crucial for avoiding collateral damage during the remediation process. We will examine how to categorize debris and biological growth, and more importantly, how to approach these challenges with industry-accepted chemicals and mechanical agitation tools. As we progress, keep in mind that the certification exam tests your ability to apply these methods in diverse, real-world scenarios. We will bridge the gap between academic theory and the grit of job site reality to ensure your knowledge is both deep and applicable. This comprehensive preparation will arm you with the confidence to handle even the most challenging system restorations while upholding the prestige of the ASCS title. I look forward to guiding you through these technical topics. See you in the next part of our discussion. Welcome back. Today we begin our deep dive into the thermodynamics and airflow principles that form the foundation of professional HVAC system cleaning. Understanding the underlying physics of air movement is not merely an academic exercise, but a practical necessity for any specialist diagnosing system performance. When we talk about airflow, we are essentially managing the transport of energy and particulates through a constrained geometry. Air, while seemingly intangible, obeys strict physical laws, most notably the relationship between velocity, pressure, and volume. You will discover how fluid dynamics, specifically the transition between laminar and turbulent flow, dictate the efficiency of particulate transport and the effectiveness of our cleaning agitation methods. By mastering these concepts, you shift your perspective from simply looking at a duct to understanding the mechanical energy required to move air through it. In any HVAC system, air acts as the working fluid that transports thermal energy from one part of a building to another, a process governed by the laws of thermodynamics. Heat naturally flows from higher temperature areas to lower temperatures, a principle that dictates how cooling and heating cycles function within your coils. We quantify this movement using the cubic feet per minute metric, or CFM, which is the volume of air passing a given point in a unit of time. However, volume alone tells an incomplete story, as we must balance it against static pressure, which is the internal resistance the system faces. Every bend, transition, and narrowing of a duct contributes to frictional losses, which act as a tax on the system's total energy capacity. The psychrometric chart is perhaps your most vital tool for understanding moisture control and preventing the conditions that lead to microbial growth. It maps the relationship between moisture content, humidity, and temperature, allowing us to predict when air will cross the dew point. When air temperature drops below this threshold, moisture condenses on surfaces, particularly on cooling coils or within cool duct interiors. This condensation provides the necessary liquid water for biological organisms to colonize, which is exactly what we aim to remediate. By analyzing the psychrometric properties of the supply air, we gain a diagnostic lens through which we can verify whether the system is operating within a range that maintains internal hygiene. When we observe how air travels, we must distinguish between laminar and turbulent flow, as both serve different functions in our trade. Laminar flow is smooth and predictable, typically occurring at lower velocities where air moves in parallel layers. In contrast, turbulent flow is characterized by chaotic eddies and vortices, which are significantly more effective at scouring debris from contaminated surfaces. Within the ductwork, we often intentionally induce turbulence during the cleaning process to lift particulates that have settled on the boundary layers. However, excessive turbulence in a poorly designed system leads to drop-offs in efficiency and increased static pressure, working against the fan's output. Static pressure measurements are the primary diagnostic method for identifying airflow restrictions, such as heavy dust accumulation or damaged internal liners. By placing probes at specific points, typically before and after filters, coils, or dampers, we can calculate the pressure drop across these components. If the observed drop exceeds the manufacturer's specifications, we know we have an obstruction that the system must overcome, costing the user energy and reducing air delivery. This is where your math skills become critical, as these measurements allow you to quantify exactly how much a system is struggling. It is a fundamental troubleshooting step that separates a technician who merely cleans from one who understands system performance. Particulate transport, or the physics of how dust and contaminants move through airstreams, relies heavily on the velocity of the air. Heavier particles settle out of the airstream when the air velocity drops below a certain point, creating the accumulation patterns you will encounter on inspection. When we initiate cleaning, our goal is to overcome the adhesive forces holding these particles to the duct wall, often using mechanical force to reintroduce them into the airstream for capture. Transporting these particles safely to our negative air machines requires maintaining enough velocity throughout the entire length of the duct runs. If the velocity drops too low in the branch ducts, you will find that your heavy debris simply moves from one spot to another rather than exiting the system entirely. The design of the ductwork directly influences every bit of the efficiency we have discussed, as every transition introduces potential energy losses. When air encounters a sharp turn or a poorly fabricated takeoff, it experiences sudden pressure changes that can lead to noise, velocity dead zones, and uneven cooling or heating. As specialists, we must recognize these design limitations because they dictate how difficult a system will be to clean effectively. Even the most powerful vacuum or agitation tool cannot compensate indefinitely for a system that is inherently choked or structurally compromised. Recognizing these limitations puts you in a superior position to provide accurate assessments to your clients regarding what cleaning can and cannot achieve. See you in the next session. Welcome to the chapter on air handling unit components, where we will deconstruct the mechanical architecture of the central air system to understand its role in HVAC performance. This module is essential for technicians who need to identify, inspect, and maintain the complex array of parts within an AHU cabinet. The housing of an air handling unit serves as the protective shell for all internal components, and its structural integrity is paramount to preventing air leakage and energy loss. Inside this cabinet, the mixing box plays a critical role by blending recirculated return air with fresh outdoor air in specific ratios determined by the building's demand for ventilation. Dampers are positioned at these intake points to modulate the volume of air entering the system, directly influencing the pressure dynamics within the cabinet. If these dampers become fouled with particulate matter, their ability to seal or modulate airflow is compromised, which often leads to inaccurate air balancing and increased motor load. Technicians must observe the condition of these linkages and actuators because even minor debris buildup can cause binding and improper air mixture, directly affecting the conditioned air quality. Movement of air through the system relies heavily on blowers and motors, which are configured differently depending on the specific application and unit design. Centrifugal fans, often characterized by a scroll or wheel shape, are ubiquitous in large AHUs due to their capability to move high volumes of air against significant static pressure. In contrast, axial fans, which look more like propellers, are usually employed in applications where air needs to be moved linearly with less resistance. The power transmission from the motor to the fan generally occurs via belt drive systems, which require meticulous alignment and tensioning to prevent premature wear. When belts are loose or misaligned, the system loses efficiency and generates heat, but they also create a perfect environment for vibration issues. Proper maintenance of these mechanical parts ensures that the fan curves remain within the manufacturer's rated specifications, preventing motor burnout and excessive energy consumption. To mitigate the transfer of mechanical noise and kinetic energy, manufacturers integrate vibration isolators and flexible connectors between the blower assembly and the ductwork. These components act as physical buffers, preventing the structural steel of the AHU from amplifying the vibrations generated by the high-speed rotational parts. Flexible connectors, typically made of high-strength fabric or specialized rubber, also allow for thermal expansion of the equipment without placing stress on the connected duct sections. When inspecting these components, it is necessary to check for cracks, tears, or hardening of the flexible material, as any breach here results in air leakage and noise transmission. Furthermore, the insulation lining the interior of the cabinet must be inspected for signs of shedding, delamination, or microbial growth, all of which can introduce contaminants into the airstream. The sequence of operation for any given AHU dictates how the unit reacts to environmental sensors, such as thermostats and carbon dioxide detectors, which are strategically placed throughout the air handler framework. These sensors provide the control boards with real-time data, allowing the system to adjust fan speeds and damper positions automatically to maintain indoor environmental quality. From a cleaning and maintenance perspective, accessibility is the primary challenge when dealing with these complex internal layouts. If components like the blowers, dampers, or heat exchangers are not easily accessible, they often escape routine inspection, leading to heavy fouling that forces the motor to work harder to overcome internal static pressure. By maintaining a clean internal environment, the specialist directly impacts the overall operational efficiency of the building, ensuring that electricity usage is optimized and the air delivered remains consistent. I look forward to discussing how these components interact with coils and drain pans in our next module. Welcome back, and let's dive into the essential maintenance protocols for coils and condensate drain pans. We will examine how these critical components influence heat transfer efficiency and overall system hygiene. Evaporator and condensing coils are the heat exchange engines of any HVAC system, yet they are frequently neglected until performance issues arise. The efficiency of these heat exchangers depends heavily on the surface area contact between the airstream and the metal fins. Over time, particulate matter and biological fouling create a layer of insulation that prevents effective heat transfer, forcing the system to work harder to achieve the same thermal set points. Fin density is a critical design factor here, as higher density creates more surface area, but also creates tighter gaps that easily trap debris and foster microbial growth. When coils become occluded with dust, pollen, or biological biofilms, the static pressure drop increases, which directly impacts the airflow volume and the fan's power consumption. Maintaining clean coils is therefore not just about indoor air quality, but about the fundamental thermodynamic efficiency of the entire air handling unit. When we arrive at a unit to clean these components, we must prioritize chemical compatibility to avoid permanent damage. Many coil cleaners are highly acidic or alkaline, which can corrode aluminum fins or copper tubing if not thoroughly rinsed or if the chemical balance is wrong. NADCA standards strongly advise the use of pH-neutral cleaning solutions whenever possible to minimize the risk of degrading the protective oxide layer on the metal. For thick, multi-row coil banks, simply spraying the face of the coil is almost never sufficient to reach the rear rows where organic material thrives. You must often employ low-pressure, high-volume water application combined with specialized tools, such as chemical foaming agents that can penetrate the full depth of the fin stack. During mechanical agitation, one must exercise extreme caution to avoid bending the fins, as distorted fins restrict airflow far more than a light coating of dust ever would. Management of the condensate drain pan is equally critical, as this is the most common site for stagnant water accumulation within an AHU. A drain pan that is improperly pitched will never fully evacuate fluids, leaving behind pools of moisture that serve as a breeding ground for bacteria and mold. Beyond the basic drainage, we have to look for the presence and functionality of secondary drain systems and float switches designed to prevent water damage during primary drain line clogs. If you find a rusted or leaking pan, it is rarely enough to simply patch the area, as the structural integrity of the metal may be compromised beyond repair. These pans must be kept clean to ensure that the moisture collected during the dehumidification process clears the unit quickly rather than becoming a source of systemic contamination. Always verify that cleaning activities do not result in moisture carryover into the downstream ductwork, as this ruins the work you have just performed. Verification of cleanliness is the final, non-negotiable step in the process, mandated by NADCA standards to prove that your intervention was successful. You should evaluate the coils not just by visual inspection, but by checking for uniform airflow and the absence of debris deep within the banks. A clean coil should look bright and metallic without evidence of oxidation or biological films, and the condensate pan should be free of standing water or organic slime layers. Documenting the condition before and after cleaning establishes the baseline required for your project reporting and ensures you have met the rigorous expectations of the field. By maintaining these components with care, you prevent the reintroduction of contaminants into the environment and keep the mechanical system operating within its design parameters. Attention to these specific details distinguishes a professional cleaning specialist from someone who simply performs surface-level maintenance. See you in the next lecture. Welcome to the chapter on ductwork materials and construction, where we will explore the structural nature of air conveyance systems. Mastering these material dynamics is essential for any professional aiming to pass the ASCS exam and perform high-quality cleaning. Understanding the material composition of ductwork is the first step in determining the appropriate cleaning methodology. Galvanized sheet metal remains the most common material due to its durability and resistance to corrosion, provided the zinc coating remains intact. However, you will frequently encounter fiberglass ductboard, which presents a far more complex challenge. This material consists of a rigid insulation board with a factory-applied foil or scrim facing on the interior. Because this surface is porous, it behaves differently under mechanical stress compared to smooth metal surfaces. When you apply agitation to fiberglass, you must remain acutely aware of the potential for material degradation or fiber release. If the integrity of the surface is compromised, the ductboard may become a reservoir for contaminants rather than a passive conveyance surface. Beyond the primary material types, the geometry of the ductwork dictates how you stabilize and agitate the system. Rectangular ducts typically utilize transverse joints and longitudinal seams that represent potential points for air leakage if sealants fail. You must inspect these junctions for gaps because air pressure loss directly impacts the efficiency of your negative pressure equipment during the cleaning process. Round ducts, by contrast, are inherently more rigid and offer better airflow characteristics, but they often utilize spiral lock seams that can be difficult to clean if debris embeds itself deep within the seam. Flat oval ducts provide a compromise between the space efficiency of rectangular systems and the structural advantages of round shapes. Identifying these configurations helps you select specialized tools, such as round brushes or specific vacuum heads, that conform to the duct profile without causing mechanical damage. Flexible ductwork poses a unique set of constraints that require a delicate hand when performing cleaning operations. While these ducts are excellent for navigating around building obstacles, they lack the structural rigidity of metal and are easily prone to kinking or tearing. If you apply excessive mechanical agitation or use brushes meant for rigid sheet metal, you risk puncturing the inner liner or causing the wire helix to collapse. This damage can permanently increase resistance in the system and lead to premature failure of the flexible duct itself. Furthermore, flexible ducts often accumulate dust in the corrugations of their inner liner, making traditional vacuuming less effective. You have to balance the need for thorough debris removal with the necessity of maintaining the structural integrity of the flexible connection. Specialized environments require us to move beyond standard materials and consider coatings that dictate how we handle microbial growth or chemical exposure. PVC-coated steel and stainless steel are frequently found in industrial applications or high humidity zones where moisture resistance is critical. These materials are generally non-porous, which makes them easier to clean extensively with water or specialized solutions, provided you respect the limitations of the coating. However, you must be cautious with the use of aggressive chemical agents that might react poorly with PVC or specifically treated surfaces. Always identify the material finish before you introduce any cleaning solution to ensure the integrity of the duct is maintained over the long term. These specialty materials are not just engineering choices, but represent critical components that maintain the hygiene of the entire HVAC system. Leakage is perhaps the most significant functional failure you will encounter when assessing a duct system for cleaning. Any breach in a duct joint, whether from degradation of sealant or physical impact, reduces the effective volume of air handled by the equipment and serves as an entry point for contaminants. When working on older systems, you will often find that gaskets and mastics have become brittle and ineffective, which complicates the setup of your negative air containment. If your negative pressure is compromised by leakage, your containment strategy will fail, potentially allowing dust and debris to migrate into occupied building zones. Therefore, a pre-cleaning inspection must include an evaluation of these sealants and joints to determine if they need reinforcement before mechanical work begins. Navigating complex configurations requires a methodical approach that prioritizes the longevity of the air system. Tight hidden runs often force technicians into difficult physical positions, but you must avoid using the ductwork itself as a structural support for yourself or your equipment. Heavy accessories or poorly supported branches can cause sagging, which leads to pooled debris and standing water in low points. You should identify these complex geometries during your assessment phase and map out an access plan that minimizes disruption to the duct structure. By understanding the intersection of material, shape, and condition, you ensure that the cleaning process provides a lasting benefit to the building air quality. I will see you in the next lecture. Welcome back to our technical deep dive into HVAC components, specifically focusing on the critical role of air filtration and the standardized MERV classification system. We will explore how different technologies function and how to properly evaluate them for system maintenance and performance. Air filtration is the primary line of defense for both the HVAC equipment and the indoor environment, yet its complexity is often overlooked. At the heart of this discipline is the Minimum Efficiency Reporting Value, or MERV, a scale developed by ASHRAE that ranges from 1 to 16. This scale provides a standardized method to quantify a filter's ability to capture particles between 0.3 and 10 micrometers. When we talk about these filters, we are primarily dealing with the mechanics of how particles are trapped as air flows through the media. Straining is the simplest mechanism, where particles larger than the openings between filter fibers are mechanically blocked. Interception occurs when particles following the airflow path come into contact with a fiber and adhere to it. Inertial impaction is effective for larger, heavier particles that have too much inertia to follow the curving streamlines of air, causing them to strike the fiber surface. Diffusion acts on the smallest submicron particles, which move in erratic patterns due to Brownian motion, increasing their statistical probability of colliding with filter media fibers. Understanding these physical mechanisms is vital when comparing different types of media, such as standard pre-filters, multi-pocket bag filters, and high-efficiency particulate air, or HEPA filters. Pre-filters serve as the first barrier, designed to capture larger debris and extend the life of more expensive, higher-efficiency downstream components. Bag filters utilize a deep, pleated surface area to maintain high efficiency while offering lower resistance to airflow compared to some rigid alternatives. HEPA filtration operates at a much higher threshold, typically requiring 99.97% efficiency at 0.3 micrometers. However, as filtration efficiency increases, the physical density of the media also tends to rise, which directly impacts the static pressure across the system. We must monitor filter loading, as the accumulation of particulate matter increases air resistance, forcing the fan to work harder, which can lead to reduced airflow and potential thermal stress on motors. Beyond mechanical filtration, we often encounter supplemental technologies like carbon filters and ultraviolet germicidal irradiation, known as UVGI. Carbon filters use the principle of adsorption to remove volatile organic compounds and odors, but they do not capture physical particulate matter and must be placed correctly in the airstream to be effective. UVGI systems are installed to neutralize airborne microorganisms, including bacteria and viruses, by damaging their DNA, but they are not a replacement for mechanical filtration. When evaluating these systems for high-sensitivity environments like hospitals or clinical laboratories, the priority shifts toward meeting rigorous regulatory requirements that dictate specific air change rates and filtration grades. In such settings, even minor installation errors, like gaps in the filter rack or poor gasketing, lead to bypass, where air travels around the filter rather than through it. This leakage completely negates the investment in high-efficiency media, as unfiltered contaminants enter the supply airstream. When you are consulting with clients regarding potential filter upgrades, you must balance their indoor air quality goals against the capacity constraints of the existing air handling unit. A common pitfall is the blanket recommendation of a higher MERV-rated filter without first verifying the system's ability to handle the resulting increase in pressure drop. If the blower motor is already operating near its limit, installing a dense, high-efficiency filter will likely trigger a reduction in total system airflow, leading to poor thermal distribution and potential coil freezing in cooling applications. Instead, suggest upgrades that maintain manageable pressure drops while targeting the specific particle sizes relevant to the building's occupants. By understanding the intersection of physics, system design, and regulatory mandates, you provide a professional service that balances air cleanliness with operational sustainability. I will see you in the next lecture. Welcome back to our exploration of HVAC system health, where today we shift our focus to the terminal components that distribute air to the end user. In this chapter, we will dissect the functional mechanics and maintenance challenges associated with VAV boxes and associated terminal units. Variable air volume, or VAV, boxes serve as the primary interface between the central air handling unit and the individual thermal zones of a building. These units modulate the volume of supply air based on the specific cooling or heating demand of a zone, which is why understanding their internal geometry is crucial for any cleaning specialist. You will typically encounter these devices above suspended ceiling tiles, positioned as the final transition point before the air enters the room through diffusers. The complexity here lies in the compact design, which often houses delicate dampers, airflow sensors, and heating elements within a very confined steel casing. When we perform system cleaning, these boxes act as localized bottlenecks where debris may accumulate, yet their mechanical sensitivity requires us to exercise significant restraint. Unlike main trunk lines, you cannot simply subject these components to aggressive agitation because damaging an internal sensor or vane can lead to chronic airflow imbalances throughout the entire zone. The internal configurations of these terminal units vary, ranging from simple single-duct assemblies to more complex dual-duct or parallel fan-powered boxes. A single-duct unit generally consists of a damper, a flow sensor, and potentially a reheat coil, whereas dual-duct systems introduce a second inlet for warm air to be mixed at the box level. From a contamination standpoint, the reheat section is often the most problematic area because moisture condensation on the coil surface can foster microbial growth over time. You must navigate the acoustic lining found inside many of these boxes, which is porous and susceptible to shedding if scrubbed with excessive force. Cleaning these surfaces requires a methodical approach, often involving high-efficiency particulate air vacuuming rather than physical brushing to prevent the degradation of internal insulation media. Furthermore, you have to be acutely aware of how these boxes interface with the building automation system, as improper manual manipulation of the actuators can override the program settings and create comfort complaints that persist long after you have finished your work. Access to these downstream components is rarely straightforward, forcing us to employ inspection protocols that rely heavily on visual verification and careful entry. Before you begin any mechanical cleaning, it is vital to coordinate with the building operator to ensure that the building automation system is aware of the maintenance activities. If you are cleaning a valve box, you might need to temporarily drive the damper to a full open position for access, but you must ensure the system returns to its original calibration point afterward so that airflow rates remain within the design specifications. Keep in mind that terminal units are specifically responsible for maintaining zone-specific thermal comfort, and even a minor misalignment of a damper resulting from our cleaning tools can cause a permanent loss of environmental control. Sensors for airflow are particularly vulnerable. They are often tiny, multi-port arrays that can be easily clogged by dust or bent during the cleaning process, rendering the box blind to the actual volume of air it is processing. Verify that these sensors are clear and calibrated before declaring the terminal unit operational, as a functional system requires both clean surfaces and accurate data feedback loops. See you in the next lecture. Welcome to the start of our chapter on exhaust systems and specialty ventilation. We will explore the critical protocols for maintaining non-supply air systems, focusing on safety, compliance, and performance. Exhaust systems differ significantly from supply air systems because they often handle air laden with contaminants, moisture, or fats that would be unacceptable in a standard HVAC delivery loop. When we talk about general exhaust, we are often managing static pressure that directly influences the pressure balance of the entire building. If a building is meant to be under negative pressure to prevent odors from migrating, a failure in the exhaust fan or a clogged riser can flip that balance, leading to unintended infiltration of outdoor air. Unlike supply systems where we worry about distributing clean air, exhaust decontamination is primarily about source removal to prevent the accumulation of hazardous particulates that could facilitate fire or create a breeding ground for biological contaminants. You must approach these ducts with the understanding that the residue inside is often more concentrated and potentially more dangerous than what you would find in a typical cooling coil or supply duct. Commercial kitchen exhaust systems represent a specific, high-risk category governed largely by NFPA 96. Unlike general ventilation, kitchen exhaust is designed to transport grease-laden vapors from cooking surfaces to the outdoors. The accumulation of these residues is a primary fire hazard, and maintenance protocols here are not merely about indoor air quality, but about life safety. You have to remove flammable deposits from hood plenums, vertical risers, and rooftop-mounted fans to prevent catastrophic duct fires. NFPA 96 dictates the clearance, access panels, and cleaning frequencies required to keep these systems within the bounds of insurance and fire marshal compliance. When cleaning these systems, you are not just brushing surfaces. You are often performing a rigorous chemical and mechanical scraping process to return the metal to bare metal condition. In laboratory or healthcare settings, the stakes transition from fire safety to the risk of exposure to high-potency chemicals or infectious aerosols. Specialty ventilation for these environments often utilizes HEPA filtration or specialized scrubbing technology within the exhaust stream before the air is discharged. When cleaning these ducts, the containment protocols must be absolute because you are dealing with a direct path from a contaminated zone to the environment. You must verify the integrity of the exhaust path, ensuring that backdraft dampers are functioning correctly to prevent cross-contamination when fans cycle off. If these dampers do not seal properly, contaminated air from one lab sequence could migrate to another area, completely undermining the engineering controls that the facility relies upon for occupant safety. The physical act of cleaning vertical risers requires careful planning regarding the location of the exhaust fan and the direction of the airflow. Most roof-mounted fans are heavy and require proper rigging, especially if you need to gain access to the discharge point for a top-down cleaning approach. You should always secure the fan via lockout tagout procedures before inserting any brush or vacuum equipment into the riser. During the process, ensure that your negative air machines are positioned to capture any dislodged debris, preventing it from being blown out of the exhaust stack onto the roof surface or into neighboring intakes. The discharge of exhausted air pollutants is strictly regulated, and you must ensure your cleaning process does not create a plume of particulate that violates local environmental codes. Ultimately, the goal is to integrate these maintenance activities into a broader facility health plan that respects the unique requirements of each exhaust type. You are responsible for identifying when a system is nearing a point of failure, whether that is indicated by increased static pressure or visible buildup on dampers and louvers that restricts airflow. Remember that the cleaning outcome is verified not just by visual inspection, but by the restoration of system performance metrics like air volume and face velocity at the inlet. This requires a diagnostic mindset where you measure the system before and after your intervention. By systematically addressing the risks of particulate accumulation and grease buildup, you ensure that the exhaust system continues to act as a reliable barrier against indoor pollutants and fire hazards. I will see you in the next lecture. Welcome to the chapter on System Inspection and Pre-Cleaning Assessment, where we examine the essential protocols for evaluating HVAC systems before any restoration begins. In this chapter, we will master the technical landscape of system assessment according to NADCA standards. You will learn the precise protocols for 10% and 100% inspections, ensuring that your evaluation is both thorough and compliant. We will move beyond visual checks to utilize advanced diagnostic tools, including robotic cameras, borescopes, and environmental measurement devices like hygrometers and anemometers. By the end of this journey, you will be capable of identifying contamination classes, diagnosing moisture-related issues, and effectively communicating your findings to stakeholders through professional documentation. Mastering these skills is not just about passing an exam, but about positioning yourself as an expert who can diagnose complex system failures with unwavering accuracy. The ability to perform a high-quality pre-cleaning assessment is what separates a technician from a true specialist. The foundation of any successful HVAC cleaning project lies in the accuracy of the pre-cleaning assessment, which is governed by strict NADCA protocols. When we talk about inspection depth, professional standards distinguish between a 10% inspection and a 100% inspection. A 10% inspection is essentially a sampling of the system's interior to assess the general condition and determine if full-scale cleaning is even necessary. During this process, you are looking for evidence of debris, microbial growth, or mechanical failure at representative points within the ductwork. Conversely, a 100% inspection requires a comprehensive end-to-end evaluation, often used when historical data is missing or when the system is suspected of severe degradation. This exhaustive approach ensures that no hidden traps of contamination or structural compromise are overlooked before the mechanical cleaning phase commences. To execute these inspections effectively, you must rely on modern diagnostic tools that allow you to reach areas otherwise inaccessible to the human eye. Borescopes and high-definition robotic cameras serve as our eyes inside the ductwork, allowing us to inspect vertical risers, elbows, and restricted spaces without dismantling the entire assembly. When navigating these spaces, pay particular attention to the internal condition of fiberglass linings. If the lining is shedding, torn, or saturated with moisture, it might be impossible to clean, potentially requiring replacement rather than restoration. We classify the contamination we find into 3 distinct levels known as classes 1, 2, and 3. Class 1 implies the system is essentially clean, while Class 2 signifies the presence of surface grime or dust, and Class 3 indicates a high level of contamination that may include microbial growth or excessive debris requiring immediate remediation. Beyond mere cleanliness, your assessment must catalog pre-existing physical damage, design flaws, and environmental hazards. You might encounter leakage at joints, collapsed duct sections, or incorrectly installed components that impede airflow or contribute to stagnant air conditions. Moisture is perhaps the most significant threat we face, as it acts as the primary catalyst for microbial colonization and fibrous insulation. By using hygrometers to measure relative humidity, and anemometers to establish airflow baselines, You gain objective, quantitative data to complement your visual observations. Documenting these specific environmental conditions is vital for establishing a baseline for future cleanliness verification. If you do not quantify the environment before you start, you have no way to prove that your efforts have meaningfully improved the system's health. Strategy development is the final, critical piece of the pre-cleaning puzzle. Once you have surveyed the system, you must determine where your entry points will be and what specific materials or tools the job will require. A complex system with limited service access demands a vastly different plan of attack than a simple, open return layout. You must consider the environmental constraints of the building occupants, such as sensitive medical settings or high-security areas that require specialized containment. Always maintain a professional perspective when communicating these findings to your stakeholders. They are not interested in the technical minutiae of your inspection, but rather the health, safety, and operational efficiency of their equipment. Clear, concise reporting that links identifiable risks to standard compliance solutions will earn you the trust required to execute the cleanup project effectively. See you in the next lecture. Welcome to this exploration of the NADCA ACR standard, which serves as the foundational pillar for professional work in air systems cleaning. We will examine the protocols governing assessment, cleaning, and restoration to ensure your projects meet the industry's highest benchmarks. The ACR standard, formally titled Assessment, Cleaning, and Restoration of HVAC Systems, is not merely a collection of best practices, but a consensus-based document that carries significant professional weight. When you operate as an ASCS, aligning your activities with this standard provides a legal and ethical framework that protects both your business and the end client. It establishes the technical expectations for what constitutes a clean system, moving us away from subjective assessments toward objective, measurable outcomes. In a professional context, non-compliance represents a serious liability, as court cases and insurance disputes often look to this specific document as the definitive authority on standard industry practice. By integrating these protocols into your project specifications and contracts, you define the scope of work with precision, which minimizes misunderstandings when the project reaches completion. This document is essentially our roadmap for consistent high-quality results, ensuring that every technician approaches an HVAC system with a uniform methodology regardless of the project's physical location or complexity. To understand the cleanliness standard, we must look at the concept of defining a successful project outcome. The NADCA ACR standard distinguishes between residential and commercial applications primarily through complexity and regulatory requirements, but the core objective remains centered on the removal of source contaminants. A project is only complete when the system meets the established cleanliness verification criteria, usually confirmed through visual inspections or non-destructive testing methods. As an ASCS, your role involves managing client expectations by using standardized language derived from these protocols, rather than promising results that fall outside the scope of mechanical cleaning. For instance, you might encounter a client who assumes that duct cleaning will magically cure all instances of poor indoor air quality. Yet our standard mandates that we clearly differentiate between mechanical hygiene and broader environmental remediation. By keeping stakeholders informed about what this standard mandates and what it does not, we safeguard our professional integrity and maintain realistic operational boundaries. The life cycle of an HVAC hygiene project starts long before the tools are unpacked, beginning with an inquiry that must transition into a formal pre-cleaning assessment. This initial evaluation is arguably the most critical phase, as it involves documenting the current condition of the system and identifying any hidden hazards or structural deficiencies that could complicate the remediation process. Once the assessment is complete and the project is underway, the ASCS must provide consistent supervision to ensure that every stage of the work follows the prescribed NADCA guidelines. Adherence to these guidelines is not a one-time event. It occurs throughout the entire progression of the job, including the final sign-off where the system is verified to be in a condition of environmental cleanliness. Because the industry continues to evolve, the standard itself faces periodic updates, necessitating that you remain informed about the latest revisions to keep your business fully compliant. Failing to stay current with these revisions is a quick path to obsolescence, as the tools, chemicals, and verification techniques cited in the standard often shift to reflect new technical research. When we discuss the integration of these protocols into your daily operations, we are talking about changing the culture of your service delivery. Contracts should contain specific language that references the ACR standard directly, which provides you with a robust defense if a customer disputes the final findings after the work is performed. When you document each step of the life cycle, inspection, cleaning, and verification, you are building a case file that proves that you discharged your professional duties according to the prevailing consensus-based requirements. This is especially important in commercial work, where system downtime must be kept to a minimum, and HVAC systems often handle critical filtration for sensitive environments like healthcare or high-tech manufacturing. The ASCS is the point person for these high-stakes environments, and your ability to articulate and apply the ACR standards is exactly what distinguishes a professional specialist from an amateur cleaner. By focusing on source removal rather than superficial surface wiping, we uphold the reputation of the industry and provide tangible value to the health and safety of the building occupants. I look forward to discussing the specifics of mechanical agitation in our next session. Welcome back. In this lecture, we begin our exploration of the core methodology known as source removal and the application of negative pressure within HVAC systems. Source removal remains the industry standard for ensuring that particulate matter is effectively extracted from an air conveyance system rather than being merely redistributed. When we approach an HVAC cleaning project, the primary technical objective is to physically remove debris from the system surfaces. To accomplish this, we rely on the fundamental principle of negative pressure, which creates a controlled environment where air flows toward our collection point. Without a properly engineered air pressure differential, we risk cross-contamination, as dust and debris could be pushed into previously clean areas or, worse, disseminated into the occupied space. This process requires not only mechanical agitation of the contaminants, but also an active collection mechanism that manages the airflow vector. By maintaining a clear path from the source of the contaminant to our filtration device, we ensure that the cleaning process is productive rather than destructive to the building environment. Engineering a robust negative pressure system starts with the appropriate selection and placement of a negative air machine, commonly referred to as a NAM. A NAM is essentially a high-capacity vacuum unit equipped with HEPA filtration to ensure that the exhausted air remains free of fine particulates. The efficiency of this system is governed by the ability to move a specific volume of air, measured in cubic feet per minute, at a velocity sufficient to transport the debris through the vacuum hose. We generally target a minimum of minus 0.02 inches of water column relative to the surrounding occupied space to ensure that any leaks in the containment or ductwork result in air entering the system rather than debris exiting it. If we cannot maintain this pressure differential, our collection strategy is compromised, and we must investigate potential bottlenecks such as undersized duct openings or improper seals. Monitoring this differential pressure throughout the entire cleaning duration is mandatory for professional practice, because system conditions change as filters load up with debris. Calculating the necessary CFM requires an understanding of transport velocity, which is the speed at which air moves through a duct or hose to keep particles suspended for easier collection. If our velocity drops too low, debris will settle out of the airstream and deposit further down the line, essentially failing the source removal objective. When selecting our vacuum hose, we must account for the inverse relationship between hose length, diameter, and the static pressure loss of the system. A longer hose with multiple bends drastically increases resistance, which forces the NAM to work harder to maintain the required CFM. Always aim for the shortest, straightest hose path possible from the cleaning site to the collection point to minimize these losses. Furthermore, the vacuum collection points must be strategically placed so that the negative pressure zone spans the entire area we intend to clean while maintaining enough strength to pull debris from the most remote reaches of the ductwork. A common point of failure in field operations is the improper sealing of the vacuum collection system or the exhaust path. If the HEPA collection unit is not exhausted outside of the building, or if the exhaust ducting has pinhole leaks, we risk reintroducing fine particulate matter into the indoor environment. We must treat the extraction path as a closed-loop system up until the final filtration stage. Should you experience a sudden loss of suction, perform a systematic walkthrough to check for popped caps, loose couplings, or accidental obstructions in the hose run. It is also important to remember that as the NAM's primary filter becomes heavily loaded with dust, the static pressure inside the cabinet increases, which inevitably reduces the total airflow volume. Experienced technicians monitor their gauges, recognizing that consistent performance demands regular filter maintenance or replacement to stay within the desired operational parameters for effective source removal. See you in the next lecture. Welcome back. Today we examine the practical mechanics of physical debris removal, specifically focusing on contact vacuuming and mechanical agitation techniques essential for meeting NADCA standards. Achieving visual cleanliness in an HVAC system is not merely about moving air. It is about the deliberate application of mechanical energy to detach contaminants from surfaces, followed by their immediate capture. When we discuss contact vacuuming, we are describing a process where the vacuum nozzle or attachment maintains physical contact with the duct wall or component surface to maximize suction at the point of release. To perform this correctly, you must select the appropriate attachment for the specific material you are addressing, such as utilizing soft bristled brushes for delicate components or rigid plastic nozzles for heavy debris on non-porous sheet metal. The goal is to create a localized zone of high-velocity airflow that pulls dislodged particulates directly into the HEPA-filtered vacuum stream before they can disperse into the airstream. This direct contact method is the most reliable way to achieve the NADCA standard for visual cleanliness, as it ensures that particulates are removed rather than simply redistributed within the ventilation network. Strategic use of manual tools like hand brushes and plastic scrapers is often mandatory when dealing with stubborn, caked-on deposits that suction alone cannot dislodge. When using these tools, you must always employ a work toward the vacuum methodology, where you agitate the debris while ensuring the vacuum nozzle is positioned immediately downstream or adjacent to the cleaning action to capture the loosened material. Neglecting this sequence often results in the migration of dust into areas you have already cleared or deeper into the system, which directly violates the principle of source removal. Corners, seams, and joints are particularly problematic because they act as traps for fine dust and biological matter that the airflow frequently misses. By using curved corner brushes or crevice tools that reach into these tight gaps, you ensure that the entire internal surface area complies with the expectations for a clean duct system. Always remember that the mechanical action must correspond to the material's structural integrity to avoid damage to the substrate itself. Mechanical agitation requires a high degree of nuance, particularly when interacting with fiberglass-lined ducting. Unlike bare galvanized steel, fiberglass insulation is composed of bound fibers that can easily degrade if subjected to overly aggressive scrubbing or high-pressure agitation. If you shred these fibers, you create a potential for airborne insulation particles and increase the surface area available for future microbial growth, which is exactly what we aim to prevent. When navigating line ducts, always opt for softer dusting brushes and maintain gentle, consistent passes that remove the debris without disturbing the underlying board material. Your tactile feedback is the most important sensor here. If you feel the material yielding or notice fraying, adjust your pressure immediately. This delicate balance between the hardness of your cleaning method and the potential for substrate damage is what separates a technician who follows the letter of the ACR standard from one who understands its spirit. Beyond the main duct runs, you will frequently encounter specialized components like sensitive sensors, air-moving blades, or heating elements that require a different level of precision. When cleaning around these objects, resist the urge to rely on heavy-duty motorized agitators. Instead, utilize manual contact methods combined with a light, steady hand to avoid bending or displacing delicate electrical connections. For electronic sensors, a soft dry brush paired with a vacuum hose positioned nearby is usually sufficient to remove surface dust without risking the calibration of the device. Speed is obviously a concern in our industry, but in the context of NADCA inspections, thoroughness must never be sacrificed for efficiency. A surface that looks clean at a distance might fail a white glove test or a flashlight inspection if the seams and components were ignored, forcing you to redo the labor. By systemizing your approach to agitation and vacuuming, you ensure quality and professional consistency. See you in the next lecture. Welcome back. Let's dig into the specialized mechanics of pneumatic whips and power brushing for effective duct cleaning. We will focus on how these tools physically interact with contaminants within various duct configurations. The fundamental principle underlying pneumatic cleaning is the use of high-velocity compressed air to dislodge particulate matter that has adhered to duct surfaces over time. When we deploy a pneumatic whip or an air skipper, we are essentially converting stored potential energy in the compressor into kinetic energy at the tool head. It is vital to understand that the air pressure, measured in pounds per square inch, must be balanced against the structural integrity of the ductwork. If the pressure is too high, you risk damaging flexible duct liners, or even breaching the seams of metal ducts, which defeats the purpose of system restoration. Conversely, insufficient pressure will leave significant debris behind, as the tool lacks the force required to overcome the adhesive bonds of the accumulated dust and biofilm. Always verify that your compressor capacity provides a consistent flow rate, as a drop in pressure during operation will lead to uneven cleaning results. Power brushing systems represent a mechanical alternative where physical contact is the primary mechanism for agitation. Unlike pneumatic whips, which rely on the turbulence created by escaping air, brushes offer a controlled method for scrubbing internal duct walls. When selecting a brush, the diameter relative to the duct size is the most important variable to consider. A brush that is too small for a large duct will fail to make consistent contact with all four sides, leaving streaks of debris, while one that is too large can become wedged or cause undue stress on the damper blades and turning vanes. You should match the bristle stiffness to the material of the duct. Softer bristles are mandatory for fiberglass ductboard to prevent erosion of the insulation, whereas stiffer nylon or wire brushes are better suited for heavy debris and unlined galvanized steel. Operating these brushes requires careful attention to the rotation speed and movement speed. Moving too quickly through a run leads to skips, while dwelling in one spot for too long can abrade the duct material. Effective duct cleaning is never a solitary action, but rather a coordinated event where agitation and collection happen simultaneously. You must ensure that your negative air machine is running at an appropriate volume to capture the debris as it is being loosened from the duct surface. This is the hallmark of the source removal method, where we avoid pushing contaminants further downstream into pristine areas of the building. In horizontal runs, long-reach tools allow us to clean deep into the system while keeping the entry points to a minimum. Remember to always work from the branch ducts back toward the main trunk line or the air handling unit. This sequence ensures that any material liberated during the process is constantly moving toward your primary collection point. Geometry plays a significant role in how you handle these tools, and you need to adapt your technique accordingly. Round ductwork requires tools that can maintain uniform pressure against the circular wall, often necessitating different whip configurations than those used for rectangular ducts. In square or rectangular ducts, the corners are the primary accumulation zones where standard agitation might struggle to reach. You might need to adjust the tool's orientation or use specific nozzle attachments that direct concentrated air pulses into those stagnant corners. Furthermore, routine maintenance of your pneumatic hoses and rotating shafts is non-negotiable. Worn fittings or kinked air lines cause efficiency losses that you might mistake for a mechanical malfunction, leading to wasted time on the job site trying to troubleshoot a tool that is perfectly fine, save for the restricted air supply. Ultimately, successful field operations depend on your ability to judge the cleanliness of the ductwork while the tools are in motion. You should approach every project with the mindset that the goal is to leave the internal surfaces of the HVAC system in a state where no loose debris can be visually detected. By monitoring your air pressure gauges and listening to the performance of your electric or pneumatic motors, you can proactively adjust for resistance as the tools move through deeper sections of the ductwork. Always prioritize the safety of the system integrity over speed, as the cost of repairing a damaged duct far outweighs the time saved by cutting corners on your agitation procedure. Consistent, methodical progress is what distinguishes a professional technician from one who merely clears the obvious obstacles. Good luck with your continued study. Welcome back. It is time to focus on the technical requirements for maintaining environmental integrity during HVAC cleaning operations. In this session, we will examine the critical practices surrounding containment barriers and negative air pressure. The primary objective of any containment strategy is the absolute isolation of the work zone to prevent the migration of dust and particulate matter into occupied spaces. We achieve this through the installation of physical barriers, typically constructed from polyethylene sheeting, which must be secured firmly to floor and ceiling surfaces using high-quality adhesive tapes. When selecting your plastic sheeting, industry standards dictate the use of a minimum of 6 mm thickness to ensure structural durability and to prevent accidental tearing during the cleaning process. Beyond simple barriers, we must address critical seals on supply and return registers or grills by covering them with plastic and sealing the perimeter edges completely. This ensures that the air handling unit remains isolated from the specific zone under maintenance, preventing cross-contamination while the system is inactive. You should always survey the site for potential gaps where air could bypass these seals, as these represent points of failure in your containment perimeter. Once the physical barrier is in place, the introduction of FUYA, negative air pressure, is the final layer of control required to manage dust movement. We utilize portable air scrubbers equipped with HEPA filters to pull air from the containment area and vent the cleaned exhaust to the exterior of the building. To ensure this system functions as intended, you must calculate the air changes per hour, ACH, which is the ratio of the volume of air handled by your scrubber relative to the volume of the workspace. A standard requirement for effective dust control often targets a minimum of 4 air changes per hour, though high-risk environments may demand considerably higher volumes. You must monitor this pressure differential in real time, typically by using a manometer, which provides a visual confirmation that the work zone remains at a lower pressure than the surrounding occupied space. If the pressure stabilizes or turns positive, contaminants will escape the enclosure, rendering your cleaning efforts counterproductive and potentially hazardous to the building occupants. In high-risk environments where contamination is significant or biological hazards are present, physical containment alone is insufficient. We must establish decontamination zones and airlocks to provide a controlled transition space for technicians entering and exiting the restricted work area. These airlocks are essentially modular enclosures designed to prevent the backflow of particulates when a door or seal is breached during entry. Furthermore, the setup and breakdown sequences are the times when containment is most fragile, so you must have your HEPA equipment operating at full capacity before disturbing any surfaces. Fire safety remains a non-negotiable consideration, as thin plastic sheeting can contribute to rapid flame spread if not treated with flame-retardant materials or positioned away from heat sources. You should always be mindful of the building's total HVAC operation, as localized exhaust fans or air handling units elsewhere in the structure can alter pressure stability within your containment footprint. Understanding these principles is vital for maintaining the efficacy of the entire cleaning project. When you consistently apply these methods, you minimize disruption and protect the air quality of the facility throughout the remediation process. See you in the next lecture. Welcome back. Today we are moving into the practical distinctions of cleaning porous versus non-porous materials within HVAC systems. When we approach an air system for cleaning, we must first categorize the internal surfaces because the material composition dictates the mechanical approach we can safely employ. Non-porous surfaces like galvanized sheet metal are generally resilient, allowing for more aggressive mechanical agitation without compromising the structural integrity of the ductwork. Conversely, porous materials such as internal fiberglass liners or rigid ductboard require a significantly more delicate touch, as these materials have a limited capacity to withstand physical force. The core principle here is that we are performing source removal, which means our objective is to extract debris while leaving the substrate intact. If we apply the same high-pressure power brushing techniques used on sheet metal to a friable fiberglass liner, we risk releasing fibers into the airstream, which is the exact opposite of our intended goal. Understanding this material distinction is the difference between a successful remediation project and one that causes secondary contamination. Fiberglass-lined ducts present the most significant challenge in the field because the insulation material often acts as a sponge for particulates and moisture. When you encounter a lining that has been compromised by moisture, you are essentially looking at an item that has reached its end of life, as porous materials do not clean to a like-new state once saturated. We use vacuuming techniques that emphasize high-volume airflow through soft, bristled agitation tools, ensuring that we do not gouge or tear the insulation surface. If the fiberglass shows signs of delamination or significant shedding, it is your responsibility to advise the client that remediation is unlikely to be effective and replacement is the only viable option. We must be particularly careful when we encounter flexible ductwork, where the fragile inner liner can easily be punctured or torn by standard rotating brush equipment. Treat every flex duct segment with as much caution as you would a delicate piece of machinery, as these components are designed for air conveyance but not for harsh mechanical stress. Managing microbial growth on porous surfaces represents the absolute limit of source removal protocols in our industry. While we can successfully vacuum and remove physical dust and debris from these liners, mold hyphae often penetrate deeply into the porous matrix, making complete removal impossible. If you identify significant microbial colonization, you cannot simply scrub the surface and expect a passing test result, because the substrate itself is contaminated. In scenarios involving wood or masonry plenums, the difficulty increases because these surfaces are inherently uneven and porous by design. We must ensure that our cleaning process maintains the integrity of the air path. Otherwise, we risk creating new, untreated porous surfaces that can foster future growth. If a porous surface must remain in service after cleaning, NADCA standards may necessitate the application of an encapsulant or sealant to prevent fiber release and further contamination. Structural integrity is a constant variable you must monitor while performing cleaning operations on any air handling system. A poorly managed cleaning process that exerts too much pressure on duct joints or plenum seams can lead to air leaks that were not present before your arrival. You need to verify that your negative air machines are providing sufficient suction to capture dislodged materials without pulling the ducting inward or collapsing flexible connections. This balance is precarious, but it is essential for maintaining the operational capacity of the ventilation system long after you leave the site. Always inspect the joints and seams after your tools have passed through a section to ensure no seals have been stripped or joints have been separated. By treating each material type according to its physical limitations, you protect yourself from liability and ensure the system operates as designed. See you in the next lecture. Welcome to this session on coil cleaning and heat exchanger maintenance. We will examine the precise techniques required to restore thermal efficiency and airflow in complex air handling systems. Cleaning an HVAC coil is fundamentally about removing thermal resistance and restoring laminar airflow across the fin surface. Particles, grease, and industrial soot act as insulators that reduce the heat transfer coefficient, forcing the system to work harder to achieve the desired temperature set point. When dealing with deep coil banks, such as those found in large institutional air handling units, a single-pass cleaning method rarely suffices. The push-pull method becomes necessary here, where you apply cleaning agents from one side while simultaneously maintaining a vacuum or extraction force on the opposite side to draw debris out, rather than driving it deeper into the fin stack. This technique prevents the compaction of dirt that often occurs during improper pressure washing attempts, which can otherwise lead to permanent airflow restriction. Selecting the appropriate cleaning medium requires an understanding of the residue encountered. For light dust, compressed air, or mild biodegradable detergents are usually sufficient, but heavy grease or baked-on industrial soot demands more aggressive chemical agents. When applying chemical cleaners, you must ensure compatibility with the coil metal, which is typically copper tubing with aluminum fins, to avoid galvanic corrosion or the pitting of base metals. Always apply cleaners from the bottom up to ensure uniform coverage and allow for appropriate dwell time as specified by the manufacturer before rinsing thoroughly with low-pressure water. Never utilize high-pressure systems indiscriminately, as they can easily deform delicate fins, thereby permanently altering the aerodynamic profile and reducing the heat exchange capacity of the unit. If fin damage has already occurred, the use of a fin comb is the only corrective measure to restore the geometric integrity of the air path. Each fin comb is sized by the number of fins per inch, or FPI, and must match the equipment specification exactly to be effective without causing further collapse. After manual inspection confirms the removal of obstructions, you should perform quantitative verification of your work. This is most accurately achieved by measuring the static pressure drop across the coil before and after the cleaning procedure. A significant reduction in pressure drop while maintaining the same fan speed is the definitive indicator of improved airflow and successful debris removal. If the coil is part of a chilled water or DX system, you must likewise ensure that the secondary side, the heat exchanger tubes or plates, is free of internal fouling that could impede heat exchange. Environmental stewardship remains a critical responsibility when using chemicals in an operating HVAC system. You must capture all wastewater and chemical runoff to prevent the discharge of contaminants into the building's drainage system or the environment. This necessitates the use of heavy-duty collection pans, drain covers, and, if necessary, portable filtration or reclamation units to manage the liquid waste stream. Before finalizing the job, verify that all condensate lines are clear and draining properly, as leftover stagnant water in a pan is a primary catalyst for microbial growth. Proper drainage management is not just a cleaning concern. It is a fundamental aspect of indoor air quality control, preventing the re-aerosolization of biological spores into the supply airstream. The complexity of these systems means there is no shortcut to thoroughness. Every manufacturer provides specific maintenance protocols that you must adhere to, particularly regarding the pH level of the cleaners being used on aluminum components. By systematically addressing the thin surfaces, ensuring clear condensate paths, and verifying performance through pressure readings, you elevate your practice from mere cleaning to professional system restoration. These methods ensure the longevity of the equipment and uphold the high standards expected of an ASCS certified professional in the field. I will see you in the next lecture. Welcome to the chapter on project documentation and reporting, where we will establish the records necessary for professional compliance. In this section, we will examine how rigorous documentation practices serve as your primary defense in liability management. In the professional life of an air systems cleaning specialist, the work does not conclude when the vacuum is disconnected or the access panels are secured. Documentation is a continuous process that begins the moment you step into a facility and extends well beyond the final invoice. You must think of your project records as an extension of your technical work. A pristine duct system without a corresponding paper trail is a professional liability waiting to happen. The objective here is to create a transparent, verifiable narrative of the project that leaves no room for ambiguity. Whether you are dealing with a standard maintenance contract or a complex remediation project, the expectations set forth by the NADCA ACR standard are clear regarding the necessity of thorough reporting. Neglecting this aspect of the job essentially invalidates the efforts you put into the mechanical cleaning process itself, as you lose the ability to prove performance. The pre-project assessment serves as your baseline and must be exhaustive in its detail. You are essentially creating a snapshot of the system's condition prior to intervention to distinguish between pre-existing damage and any future issues. This documentation must include visual evidence, typically captured through high-resolution photography or video, focusing on areas of significant accumulation or degradation. You should also record pertinent pressure measurements and airflow data, as these metrics provide numerical validation of the system's operational status. When you encounter specific points of concern, such as damaged insulation, compromised fire dampers, or evidence of moisture intrusion, these must be logged clearly. By establishing this baseline, you are protecting your company from claims suggesting that your cleaning methods caused existing defects. Consistency in this initial phase is what separates a technician from a true specialist. During the execution phase, you need to maintain a live log that reflects the scope of work performed and any necessary field deviations. It is common to encounter hidden conditions that might require a pivot from the original project plan, and these moments must be documented with precision. You should record the specific mechanical methods employed, the cleaning agents used, and any challenges that influence the final outcome. In cases where microbial testing is required, the chain of custody for all samples is absolutely non-negotiable. You must be able to prove who collected the sample, when it was collected, and how it was transferred to the laboratory for analysis. This structured approach to data collection effectively mitigates risks associated with data loss or unauthorized tampering. Implementing software tools for this purpose can significantly improve data integrity and accessibility, allowing for rapid generation of reports that clients can actually comprehend. Once the cleaning process is finished, the post-project report becomes the primary vehicle for demonstrating compliance. This document should mirror your pre-project findings, providing a side-by-side comparison that illustrates the effectiveness of your source removal methods. If physical samples or particulate counts were part of the verification process, these results occupy a central place in the final summary. You must also produce a formal certificate of completion that serves as a guarantee to the building owner that the work aligns with the specified NADCA standards. Transparency at this final stage is critical. If you identified areas where cleaning was limited due to accessibility constraints or structural integrity issues, these must be explicitly stated. Providing recommendations for future maintenance is not just a value add for the client, but a responsible way to ensure the system remains in a peak operating state over the long term. From a legal and regulatory perspective, your documentation is the most important asset you own. Should a building owner experience an HVAC-related equipment failure months after your visit, a well-structured set of records is what exonerates you from causality. Without clear data, you are essentially forced to defend your work based on memory, which holds very little weight in a dispute. Regulators, including OSHA and environmental agencies, will look at your incident reporting and hazard communication records if they conduct an audit. By treating documentation as a formal engineering record rather than an administrative convenience, you promote professional accountability across your entire organization. Consistent reporting also provides you with historical data that can help you improve your own workflows, lead times, and resource allocation for future projects of similar scale. See you in the next lecture. Welcome to our study of microbial contamination and mold biology, where we will examine the biological factors that compromise indoor air quality. In this lesson, we will focus on the environmental requirements for microbial growth and the mechanisms of colonization in HVAC systems. Microbial growth within an air handling system is not a random occurrence, but rather the result of specific environmental conditions being met. The fundamental requirements for life, moisture, a nutrient source, and an appropriate temperature range must converge for fungi or bacteria to flourish. HVAC systems are particularly susceptible because they naturally collect dust and debris, which serve as a diverse nutrient profile for these organisms. Organic materials, such as settled dust composed of skin cells, fibers, and food particles, provide the carbon and nitrogen necessary for microbial metabolic processes. While temperature is a variable, most common indoor molds thrive in the same ambient conditions that humans find comfortable, effectively making the occupied space an ideal incubator if moisture is present. We must understand that we cannot eliminate nutrients entirely in a functioning building, which shifts our priority toward rigorous moisture control and systematic cleanliness. When evaluating the risk of biological proliferation, we use the concept of water activity, or LOU, which measures the availability of water for microbial metabolism. Unlike total moisture content, water activity represents the portion of water that is not chemically bound to a substrate and is therefore accessible to a microorganism's cell membrane. Most xerophilic fungi can grow at an ADO of 0.65 or higher, while bacteria generally require significantly higher levels, typically exceeding 0.9 DO. In an HVAC system, condensation on cold surfaces like cooling coils, drain pans, or uninsulated ductwork provides the high AGO environment that allows colonies to develop rapidly. Relative humidity serves as a proxy for this environment, and keeping the indoor relative humidity consistently below 60% is a standard engineering strategy to prevent substrate moisture from reaching these critical biological thresholds. The progression of mold follows a life cycle beginning with the release of spores, which are microscopic reproductive bodies that remain dormant until they land on a suitable surface. Once deposited on a substrate with adequate moisture and nutrients, these spores germinate to form a network of hyphae, eventually blossoming into the visible structures we recognize as mold. These organisms can be transported throughout a building's ventilation network with ease, as the forced air movement inherent in HVAC operation acts as a distribution mechanism for bioaerosols. It is vital to distinguish between surface mold, which sits atop non-porous components and can be mechanically removed, and deep-seated structural contamination, which penetrates porous materials like fiberglass duct liner or acoustic insulation. Once contamination has permeated the depth of a porous material, mechanical cleaning is often insufficient, necessitating removal or professional remediation to break the cycle of colonization. Exposure to these biological agents poses verified health risks, ranging from allergic reactions to toxicological responses. Mycotoxins, which are secondary metabolites produced by certain species of fungi, can cause adverse health effects even when the organism itself is no longer viable or present. We encounter clinical descriptions of this in the form of sick building syndrome, where occupants experience acute health effects that appear linked to time spent in a building but lack a specific, identifiable cause. Alternatively, building-related illness describes specifically diagnosed diseases, such as hypersensitivity, pneumonitis, or specific infections, identified as being caused by environmental exposures within a particular structure. As professionals in air systems cleaning, our primary responsibility is source control, which means that waiting for a water intrusion event to resolve itself is never an option. Rapid physical intervention is the only way to prevent the transition from a minor leak to a widespread biological infestation. See you in the next lecture. Welcome back. This lecture focuses on the strict protocols required for the safe remediation of biological hazards within HVAC systems, aligning our practices with IICRC S520 and NADCA standards. When we handle microbial contamination, such as mold growth or sewage backflow, the primary directive is always containment. Before any physical disturbance of the contaminant occurs, you must establish an effective engineering control to prevent the migration of spores or pathogens into clean areas of the building. This typically involves the construction of physical barriers made of polyethylene sheeting, complemented by the use of negative air machines equipped with HEPA filtration. The goal is to maintain a lower air pressure within the work zone relative to the surroundings, ensuring that if a breach in the barrier occurs, air flows inward rather than allowing contaminated particulate to escape. Failing to establish this pressure differential is one of the most common precursors to secondary contamination, which significantly complicates the project scope and increases liability. Always verify the integrity of your seals and the functional status of your air scrubbers before you initiate any mechanical action. Personal protective equipment, or PPE, serves as your final line of defense, but it must be commensurate with the level of risk identified during your pre-cleaning assessment. For substantial biohazard work, such as cleaning surfaces impacted by rodent droppings or severe mold blooms, you should be equipped with at least an N95 respirator, though a P100 half-face or full-face respirator is often preferred for higher concentrations of airborne contaminants. Disposables like full-body protective suits or Tyvek coveralls prevent dust and microbial particulate from settling on your skin or your personal clothing, which could otherwise be tracked out of the containment zone. Keep in mind that the removal of PPE is just as critical as its selection, as improper doffing can easily lead to self-contamination. You must have a designated area to transition out of these suits, ensuring that hazardous materials remain within the site boundaries until they are bagged for disposal. Mechanical removal is the industry standard for remediation, as it targets the physical source of the contamination rather than relying on chemical suppression. You must prioritize the physical extraction of debris using HEPA-filtered vacuuming and controlled agitation. When we talk about fogging, it is essential to understand that this is never a substitute for mechanical cleaning. It is merely an adjunctive process. Spraying a surface with an antimicrobial while it is still covered in biological debris provides, at best, a superficial and temporary fix that violates the principle of source removal. Furthermore, the act of spraying or fogging can inadvertently aerosolize pathogens, dispersing them into the airstream if containment is not robust. Never treat contaminated porous materials like fiberglass insulation if they are saturated beyond reasonable recovery, as they must be removed, double-bagged, and disposed of according to hazardous waste regulations. Distinguishing between sanitizing, disinfecting, and sterilizing is a fundamental safety requirement in this field. Sanitizing is intended to reduce bacteria to levels considered safe by public health standards, but does not necessarily eliminate them. Disinfection goes a step further by killing a significantly broader range of microorganisms on hard surfaces, though it is not a sterilization process. Sterilization, representing the complete eradication of all microbial life and spores, is rarely needed in standard HVAC remediation and is chemically aggressive, often requiring elevated contact times or specialized equipment to achieve. Selecting the wrong agent or attempting to use a disinfectant as a cleaning agent on a surface thick with biological debris effectively renders the action ineffective. Always ensure the product label specifically lists the pathogens you are targeting and follow the manufacturer's directions regarding dwell time, which is the period the substance must remain wet to perform its intended action. Protecting occupants requires that we conduct work schedules and system operations in a way that minimizes exposure risks. During the remediation phase, the HVAC system serving the affected zone should generally be isolated or shut down to prevent the distribution of liberated spores throughout the building's air distribution network. If the system must remain functional, you are obliged to implement even stricter controls to ensure the ventilation cycle does not compromise your work area. Communication is vital here, as occupants must be informed of the nature of the work and the safety measures that ensure their environment remains secure. By adhering to these rigorous protocols, we not only protect the building's mechanical integrity, but also fulfill our professional obligation to secure the health and safety of the people relying on the air quality we manage. I will see you in the next lecture. Welcome to this chapter regarding the federal and state frameworks that govern how we interact with chemical agents during air system cleaning. We will focus specifically on the legal boundaries mandated by the Environmental Protection Agency regarding the use of antimicrobial products within HVAC systems. When we discuss the application of chemicals within an air conveyance system, we are operating within a highly regulated environment defined principally by the Federal Insecticide, Fungicide, and Rodenticide Act, commonly known as FIFRA. This federal statute grants the Environmental Protection Agency the authority to oversee the registration, labeling, and distribution of pesticides, which legally encompasses any substance intended to prevent, destroy, repel, or mitigate pests, including bacteria and fungi. It is a fundamental requirement that any product we introduce into a HVAC system must be EPA registered specifically for that use. A common misunderstanding in the field is that a product approved for sanitizing a kitchen countertop is inherently safe or legal to use inside a metal or fiberglass duct. In reality, the EPA requires site-specific registration, meaning a product must explicitly list HVAC systems on its label to be used legally. Always remember that the label is the law. Applying a product in a manner inconsistent with its label instructions is a direct violation of federal legislation. Distinguishing between an EPA-registered antimicrobial and a generic coating or sealant is critical for your professional liability. An antimicrobial pesticide is formulated to kill or inhibit microbial growth, and it undergoes rigorous testing to assess its safety when circulated through an air handler or distribution network. Coatings, conversely, are often categorized as encapsulants intended to address structural degradation or air leakage. And while they may contain antimicrobial additives, they are typically regulated differently under broader environmental and health safety rules. You must verify that any substance you apply is not just a general-purpose cleaner, but possesses a valid EPA registration number that confirms it has been evaluated for human occupancy safety. If you are ever in doubt about the status of a chemical, the EPA's Pestisec database provides clear verification of whether a product is legally permitted for interior air system applications. Using a product that is not registered for your specific intent exposes you and your client to significant potential for legal repercussions and health liabilities. The application methods we employ are as strictly regulated as the chemical products themselves, particularly regarding the use of ozone generators and chemical fogging equipment. Ozone is a highly reactive gas that, while effective at oxidizing organic matter, poses significant respiratory risks to occupants when concentrations exceed specific safety thresholds. Consequently, the use of ozone generators in occupied spaces is generally discouraged or prohibited by many industry guidelines and EPA safety positions because it is not an effective means of cleaning ducts and can cause damage to sensitive electronic components. Chemical fogging often presents a similarly problematic scenario if the delivery system results in uneven distribution or excessive pooling of liquid within the ductwork, as excess residue can become a medium for future microbial growth rather than a solution to the current one. Always prioritize mechanical source removal over chemical intervention, as the latter should only serve as a secondary strategy in a strictly controlled manner. Beyond federal requirements, you must carefully navigate the complex patchwork of state-specific licensing for pesticide application, which often exceeds the baseline demand of the EPA. Even if your equipment and chemicals are federally compliant, your company or individual technicians may be required to maintain a pesticide application license in the specific state where the work is performed. When you perform any chemical treatment, you are legally obligated to communicate this process to the building occupants, providing them with the necessary safety documentation and product labels to ensure full transparency. This communication is not merely a professional courtesy, but a risk management strategy that protects you from claims related to chemical exposure or lingering off-gassing. Off-gassing refers to the release of volatile organic compounds from the applied substance as it cures, a process that must be carefully managed through adequate ventilation before the return of occupants to the space. Legal consequences for failing to adhere to these standards are severe, and ignorance of these regulations will not protect you from liability. If you utilize an unapproved product, or if you ignore the safety intervals mandated by a manufacturer after a professional application, you risk federal fines and the potential for losing your licensure. Regulatory bodies perform regular audits, and they frequently look for documentation showing what was applied, where it was applied, and who performed the application. Documentation should include the specific product brand, its EPA registration number, and a copy of the label that dictates the application rates and drying times. By maintaining a rigorous standard for compliance, you validate the integrity of your work and your commitment to the health of the indoor environment. See you in the next lecture. Welcome to our deep dive into the application of coatings and sealants within HVAC systems. We will explore the technical nuances and industry requirements necessary to ensure these materials perform safely and effectively. Applying coatings and sealants is a practice that requires a measured, engineering-based approach rather than a simple aesthetic fix. When we discuss sealants, we are primarily concerned with two scenarios: the repair or encapsulation of damaged fiberglass lining and the sealing of mechanical joints in sheet metal ducts. In the case of damaged fiberglass, an encapsulant is used to bind the exposed fibers to prevent them from becoming airborne, effectively restoring the integrity of the insulation. With sheet metal, sealants are applied to minimize air leakage, which serves to improve the overall system's static pressure and energy efficiency. It is critical to recognize that you are not simply painting the inside of a duct. You are applying a chemical agent that alters the surface characteristics of the material. Therefore, you must ensure the substrate is perfectly clean, dry, and free of dust or debris before any product touches the surface. If the surface is compromised by grease or residual dirt, the sealant will inevitably delaminate over time, potentially causing more issues than it solves. The methods of application vary depending on the geometry of the duct and the specific properties of the coating being used. Spraying is generally the most efficient method for large, unobstructed runs of ductwork, allowing for an even, consistent buildup of the coating across the interior surface. In contrast, rolling or brushing is more appropriate for tight spaces, terminal units, or areas where overspray could inadvertently damage sensitive components. Regardless of the method, you must be hyper-vigilant about the physical operation of the system. You should never apply sealants in a way that creates bridges across moving parts like dampers, access doors, or delicate sensors. If a sealant cures across a damper blade and the actuator attempts to cycle, you risk mechanical failure or binding that could shut down the entire airflow path. Always mask off these critical components before you even begin the application process to avoid these complications. Compliance with safety standards is non-negotiable when selecting materials, specifically regarding UL 181 standards for fire and smoke ratings. A product might look effective, but if it does not possess the appropriate flame spread and smoke development certifications, it has no place in an HVAC system. We also have to consider the long-term impact on the system's thermal and acoustic properties. Adding a thick layer of coating can slightly alter the heat transfer capabilities of the ductwork and might change the acoustic dampening profile of the internal lining. Furthermore, managing the curing process is essential. You must ensure adequate ventilation through the system to speed up dry times and prevent the accumulation of volatile organic compounds. Leaving a duct damp after application creates a potential breeding ground for moisture-related issues, which is exactly what we are trying to avoid. Using antimicrobial coatings can be a valid strategy to inhibit future microbial growth. But this is a secondary step that must only occur after the source of the initial contamination has been fully removed. Durability is the final piece of the puzzle, and a high-quality application is expected to withstand the normal wear and tear of circulating air over many years. You should evaluate the potential for the sealant to crack or peel, as a failing coating can introduce debris into the airstream, which would be a failure of the remediation process itself. Regular post-application inspections are necessary to confirm that the integrity of the barrier remains intact over time. By focusing on surface preparation and application precision, you ensure that the coating serves its intended purpose without compromising the mechanical performance of the system. This technical discipline protects the asset and, more importantly, ensures the comfort and safety of the building occupants. These details are exactly what distinguishes a professional specialist from a mere technician. I will see you in the next lecture. Hello. Let's explore the chemistry and safety protocols essential for effective HVAC coil cleaning. This lesson focuses on the chemical properties of cleaning agents and the necessary precautions to handle them safely. When we approach the task of cleaning HVAC coils, we are essentially performing a balancing act between effective contaminant removal and material integrity. The primary challenge is that coils are constructed from reactive metals, usually aluminum fins bonded to copper tubing, which can easily suffer from galvanic corrosion if exposed to the wrong chemical agents. We categorize cleaners into acidic, alkaline, and neutral solutions, each serving a specific purpose based on the type of debris found on the coil. Acidic cleaners are generally effective at removing mineral deposits and hard water scale, while alkaline cleaners excel at breaking down organic, greasy, and oily residues common in kitchen or industrial exhaust environments. Neutral cleaners provide a safer, though often less aggressive, alternative for regular maintenance, where standard dust and light debris are the primary concerns. Understanding the pH scale is not just academic. It is a practical tool for ensuring that our cleaning solution does not degrade the very components we are attempting to restore. To achieve the desired cleaning result, we must look at the functional ingredients within these solutions, specifically surfactants and chelating agents. Surfactants, or surface active agents, work by reducing the surface tension of the water, allowing the solution to penetrate and lift grime away from the metal surfaces. These molecules possess a hydrophobic head and a hydrophilic tail, which enables them to surround oily particles and suspend them in the wash liquid for easy rinsing. Chelating agents, on the other hand, perform a more complex chemical task by binding to metal ions like calcium and magnesium, which are the main components of scale. By sequestering these ions, chelating agents prevent them from reprecipitating onto the coils, thereby ensuring that the debris remains in suspension throughout the cleaning process. This combined action ensures that the coil surface is not just visually clean, but chemically stripped of its parasitic biofilm and mineral layers. However, the efficacy of these chemicals comes with a non-negotiable requirement for rigorous safety protocols and the use of proper personal protective equipment. Before any chemical is even opened at the job site, you must consult the Safety Data Sheet, or SDS, to understand the specific risks, required ventilation, and spill response procedures for that particular product. Contact with concentrated cleaners can cause severe skin irritation, chemical burns, or respiratory distress, making it mandatory to wear chemical-resistant gloves, industrial-grade eye protection, and full-body aprons. If a splash occurs, you must immediately flush the affected area with water for at least 15 minutes and seek medical attention if there is any indication of ingestion or deep tissue contact. Furthermore, since these chemicals are often volatile, managing indoor air quality during the application phase is critical to ensure that vapors do not migrate into occupied building spaces. The logistics of managing cleaning chemicals on site are just as important as the application itself, as improper storage can lead to spills or accidental chemical reactions. Chemicals should always be stored in their original containers or clearly labeled secondary containers, and they must be kept within secondary containment trays to catch any potential leaks. You should never mix cleaning products, especially different brands or types, as the resulting chemical reactions could release toxic gases or produce heat that could damage equipment and injure personnel. Once the cleaning process is complete, thorough rinsing is the most critical step to prevent chemical carryover into the airstream. Any residue left on the fins will eventually become airborne once the air handler is turned back on, potentially causing health issues for occupants or leading to the slow deterioration of the metal due to prolonged chemical exposure. By adhering to these structured protocols, you ensure that the system remains both clean and structurally sound, fulfilling the professional standards expected of an ASCS. See you in the next lecture. Welcome back to our technical exploration of HVAC system hygiene. In this session, we will focus on the nuanced domain of odor control and deodorization within residential and commercial air systems. In the HVAC industry, we often encounter the misconception that odors can be permanently vanquished through the application of fragrance. As professionals, we must first internalize that source removal is the only foundational strategy for true odor control. Before applying any chemical or physical treatment, the technician must identify the root cause, which typically stems from volatile organic compounds, microbial growth, or legacy contaminants like fire-related particulates. You cannot simply mask the scent of cat urine or decomposition with a floral spray because the underlying organic matter will eventually reoffend the indoor air quality. If the system remains fouled with debris or mold, any deodorizing attempt is logically inconsistent and technically ineffective. A successful remediation plan starts with a physical cleaning to remove as much of the particulate substrate as possible before considering technological interventions. When we differentiate between neutralization and masking, we are essentially distinguishing between chemical reaction and simple olfactory distraction. Masking agents, often perfumes, do not solve the problem, but rather introduce a new set of volatile organic compounds into the breathing zone. Conversely, odor neutralizers often work through molecular modification or encapsulation, effectively rendering the odor molecule undetectable or neutralizing its chemical signature. Some systems rely on hydroxyl generators or ozone, which function quite differently by oxidizing odor-causing molecules through the release of reactive radical species. While potent, you must strictly control these technologies to prevent damage to materials or the creation of hazardous indoor environments. Always remember that ozone is highly reactive and can degrade rubber, electronics, and synthetic components within the air handling unit. Vapor phase technology offers another layer of treatment, often by introducing dry vapor compounds into the airstream to neutralize odors through contact. This is particularly useful in fire restoration projects where smoke particles have permeated porous materials throughout the ductwork. If you are dealing with dirty sock syndrome in heat pumps, which is often tied to microbial colonization of the evaporator coil, the approach must involve both deep cleaning and potential application of antimicrobial surface treatments. The persistent nature of volatile organic compounds within porous duct liners means that sometimes, regardless of your effort, source removal is insufficient. In such cases, informed communication with the client is paramount because they must understand that total removal of deep-seated odors in significantly contaminated systems is not always a realistic guarantee. You must remain acutely aware of the risks associated with chemical sensitivity among building occupants when choosing your deodorization agents. Many modern buildings are tightly sealed, meaning that any chemical introduced into the supply air will circulate until it is eventually filtered out or exhausted. You should only utilize products that are compatible with HVAC system surfaces and verify that they are applied in accordance with manufacturer specifications and NADCA standards. Over-application can lead to chemical loading, where the cleaner itself becomes an indoor air quality pollutant that causes more distress than the original odor. Always evaluate the ventilation strategy during deep cleaning to ensure the environment remains safe for inhabitants during and after the process. By prioritizing scientific methodology over convenience, you maintain the technical integrity required for ASCS certification. I will see you in our next session. Welcome to the chapter on testing and sampling air quality, where we will define the technical frameworks for validating indoor environments. We will explore how to interpret data, coordinate with other professionals, and maintain the integrity of your cleaning projects. When we transition from mechanical cleaning to environmental validation, we must rely on standardized diagnostic methods rather than assumptions. Air sampling is the most common technique used to quantify airborne contaminants, typically involving a pump that pulls air through a cassette containing a collection medium, such as a sport trap. Bulk sampling, on the other hand, requires the physical collection of material, like a piece of insulation or a section of a filter, to be analyzed in a laboratory setting for microbial identification. Surface swabbing is often used when visual contamination is suspected on non-porous surfaces, allowing for the identification of specific fungal or bacterial colonies that might not be readily aerosolized. While these methods provide concrete data, it is imperative to acknowledge that as an air systems cleaning specialist, your primary role is not that of an industrial hygienist. The industrial hygienist is the qualified professional responsible for designing the investigative protocol, interpreting complex laboratory findings, and providing medical or toxicological interpretations of risks to occupants. Interpreting laboratory results requires a nuanced understanding of environmental baselines, specifically the comparison between indoor and outdoor spore counts. A healthy indoor environment typically reflects the outdoor fungal ecology, but at significantly lower concentrations and with a similar distribution of species. If you encounter a situation where an indoor sample shows a higher concentration of a specific mold genus compared to the outdoor control sample, this often indicates an amplification site within the building. Common indoor air quality parameters, such as carbon dioxide and carbon monoxide levels, as well as temperature and relative humidity, function as primary indicators of ventilation efficiency. Excessive relative humidity is a particularly critical factor because it serves as the catalyst for microbial growth on dust and organic debris trapped within the HVAC system. You should also be familiar with particulate matter metrics, specifically PM 2.5 and PM 10, which help assess the system's ability to filter fine, inhalable particles that pose significant respiratory concerns. The marketplace is currently flooded with do-it-yourself test kits, but these tools have severe limitations that you must identify to manage client expectations. Most of these kits lack the specificity, precision, and chain of custody protocols required for professional remediation decisions, often yielding false negatives or misleading data. Relying on such tools can lead to improper decisions regarding the scope of work or, worse, failure to identify actual hazardous conditions. Your responsibility is to use third-party, laboratory-verified results to validate the effectiveness of your cleaning process, ensuring that your work has restored the system to the required standard. In high-liability environments like hospitals or clinical settings, establishing clear triggers for formal third-party testing is a fundamental requirement of your contractual risk management. You must maintain professional boundaries by delegating the diagnostic expert opinion to a certified industrial hygienist while you focus on the technical execution of the cleaning process itself. Understanding these metrics allows you to stand behind your work with the data-driven confidence that distinguishes a professional specialist from a general contractor. You are ultimately responsible for documenting that the environment has been successfully remediated according to the project specifications and environmental guidelines. By adhering to these rigorous sampling standards, you ensure that the air system does not merely look clean, but actually performs its function of delivering healthy, filtered air. This systematic approach eliminates guesswork and creates a verifiable audit trail that protects both the facility owner and your own company from potential liabilities. Always keep in mind that the goal of testing is to ensure that the air being delivered by the system is of better or equal quality to the supply air requirements of the space. See you in the next lesson. Welcome back. In this lecture, we examine the complexities of environmental stewardship and waste management protocols within the HVAC cleaning industry. Managing the waste stream generated during cleaning operations requires a systematic approach to identification, segregation, and disposal. When you perform source removal, you aren't just cleaning ducts. You are managing a collection of accumulated particulates that may include anything from household dust to hazardous materials. Effective waste management begins at the source, meaning you must categorize debris as it is collected to prevent cross-contamination. If you fail to separate standard dust from regulated materials, your entire waste load may end up being classified and charged as hazardous waste. Proper bagging is your first line of defense, utilizing appropriately rated, airtight bags or containers to seal debris during transport. Labeling these containers is not merely a formality, but a mandatory compliance step that ensures anyone tasked with disposal knows exactly what they are handling. Always assume that concentrated waste might pose an inhalation risk, making the integrity of your containment bags a critical factor in your operational safety plan. Dealing with high-risk materials such as lead-based paint debris or asbestos-containing materials demands strict adherence to both OSHA and EPA mandates. Many older HVAC systems, particularly those installed before the late 1970s, may harbor components treated with lead-based coatings or insulated with asbestos that has begun to degrade. You cannot simply vacuum these materials into a standard bag, as this would violate basic safety protocols and potentially release hazardous fibers into the air you are tasked with cleaning. When you encounter suspect materials, your assessment must prioritize containment and professional removal protocols rather than standard agitation. Always verify site-specific data or conduct testing if the age of the structure suggests the presence of these materials before starting your cleaning sequence. If you aren't certified to remediate these substances, you are obligated to subcontract the work to specialized technicians, as the legal and health liabilities for improper handling are catastrophic. Documentation becomes your primary evidence of compliance, so track every weight and destination of hazardous debris to ensure it reaches a licensed disposal landfill. The discharge of coil wash water represents a significant regulatory bottleneck that requires careful attention to local environmental laws. When you clean coils, you are likely using cleaning agents that alter the chemical composition of the water, making it unsuitable for discharge into a typical storm drain system. Most municipalities have strict sewer discharge laws prohibiting the introduction of chemicals, heavy metals, or oils into the public wastewater infrastructure without prior treatment. You must check with your local water authority to determine the permissible parameters for pH levels and chemical residues before you release any wash water. If your discharge exceeds these local limits, you must utilize a filtration unit or a containment system to capture wastewater for off-site processing. Neglecting to verify these requirements can lead to substantial fines and permanent damage to your firm's reputation within the local community. Always prioritize the capture of wash water over convenience, treating the fluid as chemical waste until proven otherwise by site-specific analysis or local permit specifications. Minimizing your firm's environmental footprint is not just a regulatory hurdle, but also an essential component of modern corporate social responsibility. A high-performing cleaning firm evaluates the life cycle of its operations, seeking ways to reduce energy and water consumption without compromising the quality of the service provided. For example, selecting high-efficiency equipment like variable speed motors for your vacuums can substantially reduce the energy load during long-duration cleanings. When it comes to mechanical components and sheet metal removed during a system upgrade, do not treat these as simple trash. Establishing a relationship with a local recycler for scrap metal and mechanical parts keeps waste out of landfills and aligns with circular economy principles. Furthermore, HEPA filters represent a significant volume of waste. Ensure that you are disposing of these according to the nature of the contaminants trapped within them. If a filter is heavily contaminated with biological growth, it must be treated as biohazardous waste rather than standard office refuse. Staff training serves as the bridge between your environmental policy and your success in the field regarding spill prevention and response. Every technician should know exactly how to deploy a spill kit and the immediate steps to take if a cleaning agent leaks or a containment bag ruptures. A proactive response strategy begins with preventive maintenance on your own equipment, such as verifying that hose connectors are secure and pump seals are intact before you enter a client facility. You should run regular drills that simulate a hazardous material leak to ensure your team remains proficient under pressure. If a spill does occur, the documentation process should be as rigorous as the cleanup itself, requiring a detailed incident report that explains the cause, the response, and the final remediation steps. This transparency builds trust with your client and prepares you for potential environmental audits, which require proof of your commitment to responsible waste disposal. I will see you in the next lecture. Welcome to the chapter on safety and regulatory compliance, where we will establish the essential framework for protected and authorized air systems cleaning operations. We will focus on the fundamental OSHA requirements that govern our field and how to maintain the highest safety standards while performing HVAC maintenance. When we approach the topic of OSHA regulations as an air systems cleaning specialist, we are essentially looking at the codified requirements for maintaining a safe working environment under 29 CFR 1910, which addresses general industry, and 29 CFR 1926, which specifically targets construction activities. HVAC cleaning often sits at the intersection of these two domains, meaning you must be prepared to navigate both sets of requirements depending on the nature of the project site. The Occupational Safety and Health Administration does not view safety as a collection of suggestions, but as a rigorous standard that employers are legally mandated to uphold. This includes the provision of appropriate protective equipment, training, and the maintenance of clear communication regarding workplace hazards. You are not just cleaning ducts. You are managing a complex site where physical, chemical, and environmental risks must be identified and mitigated before a single tool is powered on. Understanding these regulations is your primary defense against workplace incidents and ensures that your operations remain compliant with federal law. The hierarchy of controls is a conceptual framework that guides how we address hazards, starting from the most effective approach and moving toward the least effective one. At the top of the hierarchy is elimination, where we physically remove the hazard, followed by substitution, attempting to replace a hazardous process with a safer one. Engineering controls come next, which involve isolating people from the hazard through physical modifications to the equipment or the work environment itself. Administrative controls follow, focusing on changing the way people work through scheduling, training, and standard operating procedures. Finally, personal protective equipment, or PPE, is considered the last line of defense in the hierarchy because it relies on the user to correctly don, wear, and maintain gear to be effective. As an ASCS, you should always strive to engineer out risks or mandate safer work practices before relying solely on a pair of safety glasses or a respirator. Selecting and using PPE requires an understanding of the specific environment, as gear is not one size fits all. When performing duct cleaning, you are typically exposed to dust, particulate matter, and potentially biological contaminants, requiring coveralls that act as a barrier to keep these materials off your skin and clothes. Gloves must be selected based on the chemical resistance required, especially if you're applying sanitizers or handling heavy-duty degreasers often used on contaminated coils. Eye and face protection is non-negotiable when dealing with high-pressure air tools or chemical agents that could cause permanent tissue damage upon contact. Footwear standards, often governed by ASTM requirements, mandate that boots be slip-resistant and potentially puncture-resistant depending on the construction nature of your project site. Employers are legally obligated to conduct a hazard assessment to determine exactly what PPE is necessary and to provide that equipment at no cost to the employee. The concept of the right to know is rooted in the OSHA Hazard Communication Standard, which ensures that every worker has access to information about the chemicals they use daily. This is facilitated through the Safety Data Sheet, or SDS, which must be readily accessible for every substance on site, detailing safe handling protocols, emergency responses, and identifying toxicological data. Beyond chemicals, the employer is responsible for documentation and record keeping, which involves maintaining a log of work-related injuries and illnesses under specific reporting criteria. If a technician is injured or exposed to a dangerous substance, that event must be accurately captured to meet federal transparency requirements. Keeping a safe job site is also a structural habit, often referred to as housekeeping, which keeps walking surfaces clear and minimizes the risk of fire or trip hazards in confined mechanical rooms. The role of an ASCS extends beyond the mechanical cleaning process, because you are responsible for the safety of your crew as much as you are for the cleanliness of the air system. Maintaining site safety requires active daily leadership, which is most effectively implemented through daily safety briefings. These short, focused gatherings, commonly called toolbox talks, are meant to discuss the specific hazards of the day's work before the tools are removed from the truck. By explicitly stating what to look for and how to handle expected challenges, you foster a culture of vigilance. The safety officer on site holds the ultimate authority to stop work if conditions become unsafe, and your role requires you to support this mandate consistently. Consistent communication and routine safety auditing are the only reliable ways to ensure that all team members return home in the same physical condition they arrived in. See you in the next lecture. Welcome back. In this lesson, we will explore the mandatory requirements for respiratory protection when working within HVAC systems. The OSHA Respiratory Protection Standard, codified under 1910.134, is not merely a suggestion. It represents the baseline legal requirement for any technician performing air duct cleaning. When you evaluate a job site, you must recognize that respiratory hazards are often invisible, consisting of fine particulates like dust, legacy debris, or chemical residues from past coatings. The standard mandates that before a respirator is even issued, the technician must undergo a medical evaluation to ensure they are physically capable of wearing the device without compromising their cardiovascular health. This evaluation must be performed by a physician or other licensed healthcare professional to determine if the individual can safely work while wearing a respirator. You cannot bypass this step. as wearing a facepiece creates physiological stress due to increased breathing resistance. If an employer fails to provide this medical clearance, they are in violation of federal safety statutes regardless of the equipment type. Selection of the correct respirator depends entirely on the specific contaminants present, as no single mask provides universal protection. An N95 filtering facepiece is designed to trap particulates, yet it has an assigned protection factor of only 10, meaning it reduces exposure by a factor of 10. For environments where organic vapors or hazardous gases are present, such as when applying chemical treatments, you must select the appropriate chemical cartridges rather than relying on particle filters. Half-face respirators cover the nose and mouth and offer a tighter seal, while full-face respirators provide additional protection for the eyes. When hazards are particularly high or prolonged, a powered air purifying respirator, or PAPR, may be necessary to reduce breathing resistance and increase comfort levels. Always remember that the assigned protection factor defines the expected level of protection the equipment provides when used in a compliant program, so picking the wrong device renders the filtration logic moot. A critical component that many technicians overlook is the seal check and the mandate regarding facial hair. Before every single use, you are required to perform a negative and positive pressure seal check to ensure that air is flowing through the filter rather than around the edges of the mask. A positive pressure check involves blocking the exhalation valve and exhaling gently, whereas a negative pressure check requires blocking the inhalation intakes and inhaling. If your facial hair passes between the surface of the respirator facepiece and your skin, the seal is broken, significantly reducing the protection factor to 0. OSHA is explicit that any beard growth, sideburns, or even temple hair that interferes with the sealing surface is prohibited. Strict adherence to this policy is not about aesthetics. It is about preventing microscopic bypass of contaminated air into your lungs. Once your equipment is selected and your health is cleared, you must engage in formal fit testing to ensure the respirator matches your specific facial dimensions. Qualitative fit testing relies on your sense of taste or smell to detect a test agent, used primarily for half-face respirators. Conversely, quantitative fit testing uses specialized instruments to measure the actual amount of leakage into the facepiece, providing a numerical fit factor. This testing must be repeated annually or whenever you change the make, model, or size of the respirator. Beyond the testing, you are responsible for the daily maintenance, cleaning, and storage of your reusable equipment. Respirators must be stored in a clean, protected location where they will not be deformed or subjected to chemical contamination. Developing a written respiratory protection program is a mandatory administrative task for any company performing air system cleaning. This document must detail the standard operating procedures for selection, medical evaluations, fit testing, and maintenance specific to your workforce. If your company lacks this written program, you are effectively operating without the necessary infrastructure to keep field technicians compliant and protected. It is your responsibility as a professional to ensure that your respirator is properly functioning and that you understand the limitations of the protection you are wearing. By following the 1910.134 standard, you mitigate the long-term risk of occupational disease, which is the ultimate goal of these stringent requirements. Consistent compliance is far less costly than the consequences of poor lung health or regulatory fines during an audit. See you in the next lecture. Welcome to the chapter on confined space entry, where we will examine the stringent safety protocols required when working inside HVAC systems. Ensuring compliance with OSHA 1910.146 is critical to protecting personnel from the unique hazards found in restricted work areas. In the context of HVAC systems, identifying a permit-required confined space is the first step in any rigorous safety program. We are looking at spaces that are large enough for an employee to bodily enter, have limited means of entry or exit, and are not designed for continuous employee occupancy. In our field, this frequently involves large air handling unit plenums, lengthy underground ductwork, or industrial transition zones. According to OSHA 1910.146, such spaces can contain hazardous atmospheres, engulfment hazards, or internal configurations that could trap an entrant. Before any cleaning begins, you must perform a thorough physical assessment to determine if these criteria are met. If the space is identified as a permit-required confined space, you must formalize the entry process through a written permit system. This documentation is not mere bureaucracy, but a fundamental safety mechanism that dictates who is authorized to enter and what conditions must be maintained. Once a permit-required confined space is identified, the delegation of roles becomes the primary focus of your operational plan. The entrant is the person physically performing the work inside the space, while the attendant remains stationed outside to monitor the situation. The entry supervisor is responsible for verifying that all safety conditions are met before and during the entry, and they have the authority to terminate the operation immediately if conditions deteriorate. Communication between the entrant and the attendant is the lifeline of this operation and must be constant and clear. You should establish a protocol that includes predefined signals or radio checks that the attendant uses to verify the well-being of the entrant at regular, short intervals. If the attendant loses communication or suspects any distress, they must initiate rescue procedures immediately without ever entering the space themselves unless properly equipped and authorized. The atmospheric conditions within these spaces can shift rapidly, making the use of appropriate gas monitoring equipment non-negotiable. Before entry, you must calibrate and test your device to ensure it accurately detects oxygen levels, explosive gases, and toxic substances like carbon monoxide and hydrogen sulfide. Oxygen deficiency is a silent killer in confined spaces, often exacerbated by the displacement caused by cleaning chemicals or the accumulation of biological contaminants. Simultaneously, you must ensure adequate ventilation, typically by using blowers or exhaust fans to purge contaminants and provide fresh air. Proper ventilation planning requires you to calculate the volume of the space and determine the minimum air exchange rate needed to keep the atmosphere safe for the entire duration of the work. Always place your gas monitors in the breathing zone of the entrant to guarantee that the readings reflect the actual environment they are navigating. In the event that an emergency arises, non-entry rescue is the mandatory starting point for any safety strategy. This means utilizing equipment like tripods, winches, and full-body harnesses to retrieve the entrant from the exterior of the space. You must ensure that the mechanical equipment is rated for the load it might have to bear and that it is set up correctly every single time, without exception. Part of your overall project planning must include an assessment of potential physical hazards that might complicate a rescue, such as sharp duct edges, mechanical entanglement hazards from fan blades, or restricted movement due to internal baffles. Your emergency response team must be trained, briefed, and ready to act, as the difference between a successful rescue and a tragedy is often measured in seconds. Integrating these procedures into your daily job site planning minimizes the risk of injury and ensures that your workforce remains compliant with legal mandates. See you in the next lesson. Welcome back. Today, we are focusing on lockout tagout procedures, specifically tailored for HVAC systems to ensure you maintain full compliance with OSHA 1910.147 standards. Working on air handling units involves interacting with various hazardous energy sources that can cause serious injury if not controlled properly. Before you begin any mechanical cleaning or inspection, you must identify every potential energy source, ranging from electrical feeds and compressed air lines to stored mechanical energy in belts and fan assemblies. The foundation of a successful lockout procedure begins with thorough preparation and clear communication with the building facility manager or the designated site supervisor. You need to notify all affected employees that maintenance is about to occur, followed by a controlled shutdown of the equipment according to the manufacturer's specific instructions. Isolation of energy is the next critical phase, which involves physically disconnecting the power source, closing valves, or blocking pneumatic lines. Once the energy is isolated, you proceed to apply your standardized locks and tags, ensuring that each authorized person uses their own personal lock. This one key per person rule is not just a suggestion, but a mandatory safety protocol to prevent accidental re-energization while someone is still working on the system. Verification is the final step in this sequence, where you must attempt to restart the equipment or use testing instruments to confirm that the energy has indeed been dissipated and the system is truly de-energized. When dealing with large-scale projects, you will often encounter complex systems that necessitate a group lockout approach to maintain safety across multiple team members. In these scenarios, a primary lock is secured by the lead technician, or a lockbox is utilized where every team member places their individual lock to ensure the system cannot be energized until every person has finished their specific task. Remember that simply turning off the main disconnect is often insufficient because systems frequently contain stored energy that remains dangerous even after the main power is cut. You must address residual electrical charges that might be present in capacitors, as well as potential mechanical energy stored in tension fan belts or trapped compressed air within pneumatic actuators. Always follow the manufacturer's documentation for bleeding down pressure or discharging capacitors before you place your hands inside the housing or ductwork. If you are ever unsure about the isolation points for a specific piece of equipment, consult the facility's written LOTO procedures or reach out to the site's chief engineer. Documenting these specific steps for each unit is a best practice that establishes a repeatable safety baseline for your cleaning team. Training is the most effective tool for preventing accidents, and you must instill a culture where bypassing a safety lock, even for a quick check, is strictly forbidden and seen as an unacceptable risk. Employees need to understand that violating LOTO procedures carries severe legal consequences, including heavy OSHA fines for the company and potential termination of employment for the individual involved. There is never a valid excuse for ignoring a tag or attempting to work on a live system, as the primary goal of the ASCS is to clean the air system without jeopardizing human safety. Once your cleaning work is complete, the restoration of energy requires its own systematic set of procedures to ensure everyone is clear of the equipment before the system is brought back online. You must remove all tools and debris from the internal components, replace any access panels or guards you remove during the process, and notify the facility manager that the equipment is ready for testing. Safety is paramount in our field, and adhering to these rigorous lockout standards ensures that we leave the facility in exactly the same state of operational readiness as we found it. I will see you in our next session. Welcome back. Today we delve into the critical aspects of fall protection and ladder safety, which are non-negotiable requirements when performing duct cleaning operations. Working at height is a daily reality for an air systems cleaning specialist. Whether you are accessing roof-mounted air handling units, inspecting mezzanines, or navigating suspended ceilings, the primary principle here is to recognize the elevation triggers established by OSHA for fall protection. In general industry environments, the requirement to provide fall protection begins at 4 feet, whereas in construction settings, the threshold is 6 feet. This distinction is vital because a duct cleaning contract might fall under either classification depending on the nature of the project. If you find yourself working on low-slope roofs, you must be particularly vigilant about the installation of guardrail systems or the establishment of clear warning lines that prevent accidental encroachment onto an unprotected edge. These physical barriers are your first line of defense against gravity, and failing to respect these boundaries significantly increases the risk of a life-altering event. When it comes to portable ladder safety, the industry standard relies heavily on the three-point contact rule. This means that at any given moment, you must have 2 hands and 1 foot, or 2 feet and 1 hand, in firm contact with the ladder rungs or side rails as you ascend or descend. Before you ever set foot on a ladder, you are obligated to perform a thorough inspection of the equipment. Look for broken side rails, missing or damaged rungs, and mechanical failure in spreaders or locking devices on step ladders. For extension ladders, always ensure you have the proper overlap between sections based on the manufacturer's specifications and that the base is set at a safe angle, typically a 1:4 ratio. Stepladders must never be used in a partially closed position, and you should never stand on the top cap or the highest step, because reaching too far from the center line of the ladder will destabilize it. Sometimes you cannot rely on ladders alone, which leads us to personal fall arrest systems, or PFAS. A complete PFAS consists of 3 essential components: a full-body harness, a shock-absorbing lanyard, and a secure anchor point. A harness is only effective if it is fitted properly to your body, meaning it must be snug enough to distribute forces evenly across your thighs, pelvis, and shoulders during a fall. The lanyard connects your harness D-ring to an anchor point capable of supporting at least 5,000 pounds per employee attached. If your lanyard is equipped with a self-retracting lifeline, ensure it functions smoothly without slack that could lengthen a potential fall distance. Always verify the integrity of your anchor point before you start your work, as even the most expensive harness is useless if the structure it is attached to pulls away from the building framework. Floor openings, skylights, and attic hatches are common, yet frequently overlooked hazards in large facilities. A skylight that is not rated for the weight of a technician can fail instantly, leading to a catastrophic fall through the ceiling. You should treat any hole on the surface walking area as a fall hazard that requires a cover capable of supporting twice the weight of any equipment or personnel that might cross it. These covers must be secured against accidental displacement and clearly marked with warnings. If you are operating aerial lifts or scissor lifts, remember that these are not just simple platforms, but pieces of heavy machinery requiring pre-work inspections of hydraulics, emergency controls, and safety sensors. Always wear a harness attached to the manufacturer's specified anchor point inside the platform to prevent ejection if the lift is bumped by moving equipment. Recognizing hazards is a cognitive skill that complements your physical safety protocols. Before starting any job, survey the area for uneven roof surfaces, slick metal decks, or loose debris that could cause a trip leading to a fall. If you are unsure about the load-bearing capacity of a ceiling or a mezzanine deck, do not proceed until you have confirmed it is safe. Proper training extends beyond knowing how to use a harness. It involves the ability to set up your safety equipment in a way that minimizes potential fall distance and ensures a clear path for rescue in the event of an emergency. Preventing injuries from falls during duct access requires constant vigilance and an unwavering commitment to these standard safety practices throughout your entire scope of work. I will see you in the next lesson. Welcome back. In this lecture, we examine the complexities of hazard communication and the globally harmonized system as they apply to your daily work with HVAC cleaning chemicals and agents. The Occupational Safety and Health Administration's Hazard Communication Standard, codified under 29 CFR 1910.1219, serves as the bedrock for chemical safety in our industry. Its primary purpose is to ensure that the hazards of all chemicals produced or imported are evaluated and that this information is transmitted to employers and employees. When you perform air systems cleaning, you are regularly utilizing diverse substances ranging from coil cleaners to antimicrobial coatings. This standard requires that you not only identify these chemicals, but also understand the specific risks associated with them. The Globally Harmonized System, or GHS, provides the standardized framework for this communication through consistent labels and safety data sheets. By adopting these international standards, we move away from fragmented regional labeling systems toward a singular, predictable method for conveying hazards. A consistent approach is not just a regulatory checkmark, it is a fundamental component of maintaining a safe working environment in the field. Ignoring these protocols risks both personal injury and significant legal noncompliance for your firm. Central to this communication is the safety data sheet, which moved from the older material safety data sheet format to the standardized 16-section GHS structure. Every technician must know how to locate and interpret these documents for every cleaning agent, sealant, or biocide stored or used in the facility. Section 2 of the SDS is particularly critical as it identifies the specific hazards, signal words, and the required GHS pictograms. You must be able to recognize symbols like the flame for flammable materials, the skull and crossbones for acute toxicity, or the health hazard silhouette, which often denotes carcinogens or respiratory sensitizers. Beyond just reading these documents, your company must maintain an accurate and up-to-date chemical inventory. If a chemical has been phased out of your project usage, it should be removed from the inventory and properly disposed of according to local environmental regulations. Accessibility of these sheets is a legal requirement. Having a digital folder or a physical binder at the job site is the expected industry standard. When we consider the practical application of labeling, the GHS requires that all containers, whether primary or secondary, are appropriately marked if the chemical is moved from its original manufacturer vessel. Your labels must indicate the product identifier, signal words like danger or warning, hazard statements, and precautionary statements. This ensures that even if a container is unlabeled by mistake during a busy shift, any technician on site can immediately discern the risk level. Beyond internal safety, we also face the responsibility of communicating these risks to other trades working in the same vicinity and to building occupants who may be sensitive to air quality changes. If your cleaning process involves high VOC chemicals or biocides, clear signage and coordinated schedules are necessary to prevent unnecessary exposure to building staff. This transparency is a legal obligation under the requirement to inform downstream users of the chemical hazards present in the work environment. Failure to coordinate can lead to accidental exposure incidents that are entirely preventable through simple communication. Beyond labeling, we must address the specific management of pressurized cylinders and flammable substances, which are common culprits in shop and site accidents. Pressurized containers must be stored upright, secured to prevent tipping, and kept away from extreme heat sources. When using flammable cleaning solvents, assume that the vapor can travel and find an ignition source, even if you do not see an immediate flame. Your hazard communication plan should explicitly detail the emergency protocols for chemical exposure, including eye wash station locations and skin decontamination procedures. All team members must be trained on these specific hazards before they ever pick up a sprayer or a whip tool on a live project. This training is not one-time learning. It should be refreshed whenever a new substance is introduced to the company's cleaning inventory. Documented training records are your primary defense in showing that you have met the duty of care expected of an ASCS professional. Integrating these safety elements into a cohesive plan requires a shift in how we perceive chemical management as part of the overall job workflow. It is easy to view these regulations as administrative friction, but they actually provide the structure required for professional liability protection and operator well-being. By maintaining transparency through consistent labeling, diligent SDS management, and frequent training, you safeguard your workers and the reputation of the organization. Each chemical you handle must be viewed through the lens of its physical, health, and environmental classification, prioritizing the least hazardous alternative whenever the project specifications permit. Establishing this culture of safety documentation ensures that when something does go wrong, such as a spill or an accidental skin contact, the response is automatic rather than panicked. This level of preparation is what separates a true specialist from someone who simply operates equipment. See you in the next lecture. Welcome back. In this lecture, we will examine the critical protocols for electrical safety and the proper handling of power tools within the HVAC cleaning environment. Working in the field often requires us to interface with various pieces of equipment, ranging from industrial-grade vacuums to air compressors and handheld pneumatic devices. Given the environment we operate in, electricity is omnipresent, yet it is often treated with complacency. The primary risk is, of course, electrical shock, which can occur when a person becomes part of a circuit, especially when working near air handling units or electrical panels. We must insist on the use of ground fault circuit interrupters or GFCIs on all job sites to mitigate the risk of electrocution. A GFCI works by detecting a ground fault, a path for current to leak, and cutting off the power almost instantaneously before a fatal current can pass through the technician. These devices are non-negotiable when using power tools in environments that are often damp or metallic, such as mechanical rooms or near cooling coils. Before you even plug in a tool, you have an obligation to perform a thorough visual inspection of the entire power delivery path. Frayed, cracked, or brittle insulation on cords acts as an open invitation for hazardous conditions, particularly in tight ductwork environments where wires are prone to pinching. It is a common, yet dangerous practice to rely on long-run extension cords as a substitute for permanent wiring. You must avoid this, as permanent circuits require proper routing and protection that extension cords were never designed to provide. Additionally, understand that the ductwork itself is not merely a transport mechanism for air, but potentially a site for static electricity buildup. In environments where dust concentrations are high or where flammable contaminants might be present, effective grounding of the vacuum and agitation equipment is essential. Without a proper path to ground, an accumulation of static charge can spark, potentially triggering an ignition if the right atmospheric conditions exist. Pneumatic tools demand their own specialized set of safety considerations, as they combine the kinetic energy of air pressure with the dangers inherent in high-pressure delivery systems. High-pressure hoses must be inspected for bulges, soft spots, or compromised fittings that could result in a catastrophic hose failure. Always ensure that the pressure ratings of your hoses align precisely with the output of your compressor and never bypass safety valves that are there to prevent overpressurization. When moving outside to rooftops or elevated positions, the danger is amplified by the presence of overhead power lines. These lines are rarely insulated in the way household wiring is, and coming into proximity with them while holding metallic extension tools or aluminum ladders creates a massive risk for arcing. Always perform a situational assessment before raising any equipment. maintaining the required minimum clearance distances to keep yourself and your crew safe. To ensure you are operating within professional and legal boundaries, always refer to NFPA 70E, which acts as the gold standard for electrical workplace safety. This document provides a framework for identifying hazards and conducting risk assessments, which is vital when you are opening up electrical panels to service localized components. Compliance with these standards is not merely about avoiding fines. It is about establishing a rigorous culture where maintenance is predictive rather than reactive. Every power tool should be on a maintenance cycle that includes checking the integrity of the housing, the function of the switches, and the overall stability of the connectivity points. If a tool shows signs of distress, it must be tagged and removed from service immediately until it is deemed safe by a qualified person. By adhering to these disciplines, you ensure that your focus remains on the quality of the cleaning rather than on avoidable site accidents. I will see you in the next lecture. Welcome back. In this chapter, we will focus on verifying that your work meets NADCA cleanliness standards, ensuring the system is truly returned to a hygienic state. Post-cleaning verification is the definitive step that separates a professional intervention from a superficial dusting. According to the ACR standard, the primary objective is to verify that the internal surfaces of the HVAC system are visually clean and free of loose debris. We rely heavily on the visual inspection method for non-porous surfaces, which serves as the industry benchmark for confirming that our source removal techniques were effective. When you perform a visual inspection, you are looking for more than just a lack of visible dust. You are checking for an absence of construction debris, biological growth, or unexpected contaminants that survive the cleaning process. If any area fails to meet these criteria, it is your responsibility to document the failure and immediately perform re-cleaning of that section until the standard is satisfied. Always remember that the burden of proof lies with the service provider to demonstrate that the system meets the established cleanliness benchmarks before closing out the project. One of the more nuanced tools in our arsenal is the surface comparison test, commonly referred to as the SCT. This test provides a structured way to evaluate cleanliness when visual inspection alone might be subjective or difficult to quantify. By using a white filter or a collection media to wipe a representative surface, you create a tangible record of the cleanliness that can be compared against a standard. It is not necessarily a laboratory-grade forensic analysis, but it provides an objective indication of the residual debris levels remaining on a surface after your agitation and vacuuming. If the test results indicate accumulated debris beyond the acceptance limits, you must return to the cleaning phase for that specific zone. This process should be applied consistently across different representative locations within the system to ensure that your cleaning quality is uniform throughout the entire supply and return air network. Beyond visual metrics and surface testing, forensic verification can involve vacuum sampling if the situation calls for a higher level of scrutiny. Vacuum collection entails taking a surface sample over a defined area and analyzing the collected material, which allows you to establish a quantitative baseline for the system's hygiene. This method is particularly useful in environments where clinical cleanliness is required or when there is a dispute regarding the efficacy of the previous cleaning efforts. High-resolution imagery is your best ally during these documentation phases, as clear photographs provide an undeniable record that you can present to the building owner. By capturing images before and after the cleaning, you build a trail of evidence that validates your process and protects your firm's reputation. Clear documentation is not just about compliance, it is about providing the building owner with the peace of mind that their occupied space is served by a properly maintained system. Managing the final inspection with the building owner or a representative is a critical component of professional project management. You should walk the client through the system, focusing on key access points that were utilized during the cleaning process, and allow them to witness the cleanliness firsthand. This collaborative approach minimizes the risk of post-project complaints and facilitates a smoother sign-off procedure. During this walkthrough, you must also verify that all access panels have been properly reinstalled, properly sealed, and that the system's air integrity has been restored. Failure to ensure a tight seal on access doors can lead to significant energy loss and potential bypass of filtration, which defeats the purpose of the cleaning. Always perform a final operational check of the system's mechanical components, such as fans, dampers, and valve boxes, to ensure that the physical act of cleaning did not disrupt any delicate movements or control signals. Finally, the project concludes only when the system has been returned to its intended operational state and verified to be free of any secondary contamination. You must ensure that all tools, containment barriers, and secondary waste materials have been completely removed from the mechanical space to avoid introducing new particulate matter into the system. Leaving behind debris, such as filter media scraps or cleaning agents, is a common pitfall that can lead to recontamination of the supply air almost immediately after startup. A verified clean air system is the result of meticulous planning, disciplined execution, and a rigorous adherence to the verification protocols we have discussed here today. By closing out the project with a thorough final testing phase, you demonstrate a level of professionalism that aligns with the requirements of an air systems cleaning specialist. Your final goal is a system that not only looks clean, but is mechanically and hygienically sound, providing optimal performance for the building occupants. See you in the next session. Welcome back. In this final session, we will synthesize our knowledge of HVAC systems, NADCA standards, and safety protocols to ensure you are fully prepared for the certification examination. To master the certification exam, you must move beyond rote memorization and begin thinking like a professional who understands the governing principles of air system hygiene. We have covered the science of thermodynamics and the mechanics of airflow, both of which are central to how contaminants move through an HVAC system. When reviewing CFM and static pressure calculations, focus on the relationship between duct resistance and fan performance. A common point of confusion involves the interplay between total external static pressure and the efficiency of negative air machines. Remember that the ACR standard is designed to provide a baseline for cleaning efficacy, and understanding why we perform a source removal rather than a simple sweep is a fundamental competency. As you review your notes, ask yourself how each technique, from mechanical agitation to contact vacuuming, directly addresses the removal of particulate matter without damaging the substrate. Chemical applications and microbial remediation represent a significant portion of the assessment, and you should be comfortable with the regulatory landscape dictated by the EPA. You are expected to know the difference between sanitizers, disinfectants, and fungistatic agents. If a project involves mold remediation, your adherence to OSHA standards for respiratory protection and containment is not merely a recommendation, it is an absolute requirement of the ACR standard. Ensure you can distinguish between porous and non-porous surfaces, as these material types dictate the permitted cleaning methods and the potential need for replacement. Reviewing your understanding of GHS labeling and the hierarchy of controls for hazard mitigation will prevent you from missing easy points on safety sections. The goal is to internalize these safety habits so they become second nature rather than something you have to verify in a reference manual under pressure. When you sit for the exam, your strategy for answering multiple choice questions is just as important as the depth of your technical knowledge. You will likely encounter questions that ask for the best answer, which implies that multiple options could technically be correct, yet one is superior due to safety, efficiency, or adherence to the NADCA standard. Begin by eliminating the clearly wrong choices, and then evaluate the remaining options based on the specific constraints of the prompt, such as confined space requirements or ventilation limitations. Managing your time effectively means that if you find yourself stuck on a complex calculation, you should mark it for later review and move on to ensure you do not miss easier questions. Treat the exam as an opportunity to demonstrate your professional judgment, which is precisely what the certification body aims to measure. Do not second-guess your experience when the answer aligns with the protocols we have discussed, especially regarding project documentation and reporting. Finally, let us discuss the trajectory beyond the exam date and how to maintain your standing as a specialist. Achieving your status is just the first step in a career that requires constant updates as technologies and environmental regulations evolve. Continuing education credits are not just a bureaucratic hurdle. They serve as a mechanism for you to stay current with the latest research in indoor air quality and ventilation science. Developing a personal study plan involves identifying your weakest areas from this course and dedicating time to them before you schedule your test. Think about the practical application of these standards in the field, as the exam writers often mirror the real-world complexities technicians face on a daily basis. By maintaining this professional mindset, you will find that the exam is a validation of your preparation rather than an insurmountable barrier. Preparation is the silent partner of competence. Good luck with your final preparations, and I will see you on the other side of your certification success.